Like I am live. Okay. Hello, wonderful people of the internet. Welcome back to another episode of Leo's Lab. So today I'm doing something a little bit different. We're actually going to do a lecture series on GPU computing. And today will be the first lecture where we're talking about just all the different ways in which you can do GPU computing, a bunch of different programming abstractions that you could use. We discuss a bunch of different programming languages. We actually get down and dirty and do the programming. And I even have an example that shows literally 1,000 times speed up for using the GPU versus not using the GPU. For people who might be just coming in and you've never seen a video from me before, like you maybe found the VOD or whatever via just searching on YouTube or whatever, hello, I'm Dr. James Schloss. I got my PhD from the Okinawa Institute of Science and Technology Graduate University back in 2019, where I did quantum simulations on GPUs. That was kind of the main thing that I did. Since then, I've been working in and out of the Julia lab. It's kind of like the research arm behind the Julia programming language. Not the only research arm, but probably the biggest one. And I think it's where the Julia lab was, the Julia language was actually developed. For those who don't know Julia, it's okay. We'll talk about it a little bit later when we talk about like GPU languages and stuff like this. But suffice it to say that I have been working on the GPU ecosystem in Julia. That is to say, I have directly contributed to a lot of the major packages, that is kernel abstractions, Julia GPU arrays, this type of stuff. Now, am I the main developer? No, not by a long shot. There are other people who are like 100 times better than I am in pretty much every way. But I would say I'm one of the primary users of the GPU ecosystem in that, sure, maybe I'm not like the biggest developer of kernel abstractions or GPU arrays, but I'm kind of one of the people who are using it for scientific computing and kind of pushing what you can do in the ecosystem. So, for example, I've done climate simulations, I've done molecular dynamics simulations, and all this kind of stuff. For the most part, my research interests are all related to the GPU as well. And so, long story short, if you're listening to me and you're asking, does this person know what they're talking about? The answer is probably no, but I do have 10 years of experience in GPU computing, and so I'm hoping that this lecture series is useful to a large number of people. In addition, I'm writing a book, and that book is known as the GPU Kernel Handbook. It's available here on laoslabs.com/GPU-handbook. It's available in the link below. For those on YouTube, and for those on Twitch, I'll go ahead and post a link here, and I'll also post it over here in chat as well. That way, if anybody's like watching it, and there's like a live playback or whatever, you guys can see it there as well. There's a lot of stuff here. We have an introduction where we talk about basically everything there is to know about GPU computing, like the ecosystem, all that kind of stuff. And then I just recently put out a chapter called All the Ways to GPU, where we talk about basically just getting your foot in the door, starting things out, talking about the different abstractions you can use and all this kind of stuff. So this is kind of more or less the material that we'll be working with today. So I guess we can go ahead and get started, unless anybody has anything that you guys want to talk about beforehand, but I think we're good to go. So as an overview, here's kind of what we want to talk about. We want to talk about a survey of GPU computing as it is right now. We talk about languages, abstractions, all that kind of stuff. Then we want to talk about like actual installation of the language that we have chosen to do this work in. Then we talk about 3 different abstractions, different ways in which we can do GPU computing moving forward. I'm hoping to keep this entire thing to roughly an hour. We'll see how that goes. Again, it's mainly going to be hopefully informative for people who jump in. There might be a little bit of chatter here and there, but for the most part, I'm trying to focus on one specific thing and talk about that thing. So first, let's talk about what is GPU computing. So in the GPU book, I wrote the following. I said, the GPU is a separate device that is built to solve a lot of simple operations at the same time. So let's just go ahead and grab this line and let's talk about what that means. So the GPU is a separate device that is built to solve a lot of simple operations at the same time. So what does this mean? Well, GPU stands for graphics processing units. It has primarily been used to do graphics, right? This could be anything from CGI, for movies. It could be just basic video games. It could be any number of things, right? And so let's just talk about a very basic workflow that you might imagine. We have a screen that is high definition, so that means 1920 by 1080. I am aware there's much higher definition screens that we can get nowadays, but let's just assume it's 1920 by 1080, which means we're talking about on the order of 2 million pixels, right? Now let's say we have a very simple operation where we just want to shade all of the pixels like red or some other color. Maybe it's a gradient or something. It doesn't really matter. The fact is we just want to shade all of these pixels. To do that, we use what's called a shader. And in particular, we'd be using what's called a fragment shader, in that we're shading all we will be shading what is essentially a giant square that represents a screen based on like what we want each pixel to be, okay? Now, the operation, i.e. coloring a single pixel, is not super complicated. It's relatively straightforward to do. And so we don't necessarily need to do one at a time because they're probably all independent. So we can do all of them in parallel if we want, or many of them in parallel if we want. And we just kind of do a very simple operation all over, like just a whole bunch of very simple operations. And we do as many of those operations at the same time as we can, right? So let's dive into the reason as to why you want to use GPU computing, right? So first things first, I think most people nowadays understand the utility in GPU computing. Like pretty much every AI model is, trained on a GPU. I mean, NVIDIA is like the richest company on the planet right now, specifically because of their usage of NVIDIA GPUs for AI and training AI and all this kind of stuff, right? Supercomputers, the fastest supercomputers in the world, they all run GPUs. If you're just trying to do graphics or anything like that, which is a big application, a lot of people want to do game development, you're going to be using the GPU for that. There's so many different things that you want to use a GPU for. I would even argue that GPUs nowadays are more important to know than CPU programming. Sure, yeah, you will use CPU programming every now and again, but for most of the workflows that I've been doing, like, it just makes sense to do them on the GPU. Why? Because the GPU, though it was originally intended to do very simple operations, and it still does very simple operations, we as programmers have become better at using the GPU, and the hardware has become better such that now pretty much anything that you would want to do on the CPU, you could do faster on the GPU. And this is why we see a lot of trends for like GPU computing in, like, for example, Apple Silicon, where the GPU is in a sense more accessible than it was before. We have more cores available. I mean, nowadays, pretty much nobody is writing code for like a single core CPU. That just doesn't happen. It's not very common. There might be some embedded systems where this happens, but for the most part, when people are programming, they have multiple cores available to them. And so thinking about parallelism, how to use all of these cores effectively at the same time is a big deal, and it's something that we should be focusing on as programmers, right? And so when you put this all together, it seems to me that GPU computing, the ability using your GPU for basic computation, general purpose computation, is one of the things that I think a lot of people should focus on, or they should know. And yet at the same time, I feel like the area of GPU computing, is kind of like siphoned off. It's something that you don't really learn about until you're maybe a grad student. And I've heard multiple people tell me that, GPU computing is too complicated to teach to undergraduates. But I don't necessarily see that as true. And in my opinion, GPU computing is relatively straightforward, right? I'm not going to say it's easy, but relatively straightforward and could be taught to undergraduates as long as you do it in the right way. Don't necessarily teach like GPU computing after you've learned all of CPU stuff. No, teach it at the same time you're learning the CPU. And as long as they're taught at the same time, it should be relatively straightforward to learn these additional abstractions along with, your time in which you're learning CPU programming and stuff like that. Hey, Marion. Hey, Kaz Games. The terminology really confuses me. Fragment, uniform, vertex buffers. Yeah, 100%. I will say that a lot of this terminology is particularly rough in the graphics APIs, and we're going to be focusing on compute APIs. And we can go ahead and talk about what the difference is between compute and graphics. Actually, that's a good thing to talk about next. Compute versus graphics. That's a great thing to talk about. 1920 by 1080 is the number of CPUs. It's not necessarily the number of CPU cores, nor is it the number of GPU cores. At the end of the day, it will be kind of scheduled so that if you have 2,000 pixels to color, it'll color as many of them as you can in parallel at the same time. So as we learn GPUs, we should create analogies with the CPU. I think it's actually kind of the other way around. Like, it's not necessarily that we should. I think one problem that people have when they teach GPU computing is they spend so much time relating it to CPU computing, right? The assumption is that you already have a good understanding of CPU computing, and you need that fundamentally before hopping into GPU computing. And my argument is, it's okay. Let's start with GPU computing. Sure, there's some basic things that you might need to know from your CPU land, but really, the abstractions are so fundamentally different, you don't really need to know that much in order to hop into GPU computing. You can kind of start like more or less from scratch. So as you're learning CPU computing and you're learning these abstractions, we can add GPU computing as an additional abstraction to learn. So one CPU will do one pixel, one GPU will do a lot of pixels. Well, one CPU core will do one pixel. Well, okay, let's talk about the difference between CPU and GPU right now. CPU versus GPU. All right, that's the thing we're talking about now. So the CPU typically has on the order of, 12 cores. I have a 12-core machine. Used to be 4-core was a lot. You know what I mean? 2-core was a lot at some point. The CPU's, hardware stack, whatever you want to call it, is designed in such a way that it is intended to do essentially computation as fast as possible. It does one thing and then another thing and then another thing and another thing, right? It's intended to be a very, very strong, beefy core. I don't know how to put this. The idea is that like you go through computation as quick as possible, right? The GPU, on the other hand, has, you know, thousands of cores available at any given point in time. And so the real kicker here is that for CPU computing, you typically focus on one item at a time, whereas for GPU computing, you always focus on parallelism first, right? And that's kind of the big difference between the two of them. The GPU is useless if you focus on only one core. You really have to focus on multiple cores all working at the same time. And we'll talk about that actually later today with an example that I want to show off to show how to get performance out of the GPU. The fact is, if you're doing very simple operations, unless you're doing a lot of these simple operations, the GPU doesn't really give you much benefit, right? You really need to find a way to transform these complex operations that you're already doing on the CPU into like a bunch of itty bitty little pieces that you can distribute onto the GPU to make use of it, right? To, of course, still high end. I think that's true, right? I think like 8 core is probably normal nowadays. It's basically doing a function on a pixel, which means there's no sequential programming. Yeah, that's actually one of the things I wanted to point out here. So let's actually detail this sentence right here. The GPU is a separate device that is built to solve a lot of simple operations at the same time. Okay, this actually has like kind of 3 inbuilt. Oh, I did not mean to turn that whole thing red. Let me change it back to white. This has kind of 3 like claims being made at the same time. So first of all, the GPU is a separate device. That's the first thing we need to talk about. It is a separate device, right? It's built to solve a lot of simple operations, right? And then at the same time, right? So these are kind of the 3 things we want to talk about. So one, the GPU is a separate device. We should talk about this, right? It seems normal, right? Like if anybody has built a computer before, they know that you take your GPU, you slot it right into the PCIe slot for your motherboard, and very clearly it is a separate device. It is something different than the CPU, right? If you want to send data to the GPU, what you have to do is you have to take the data that's on the CPU RAM and pass it through the PCIe slot into the GPU RAM, you know, wherever that happens to be on the GPU. This actually has some lasting consequences to how you do GPU computing. You always have to recognize that the transfer step, the time it takes to like kind of turn the GPU on and off again, the time it takes to send data from the CPU to GPU is always going to be the slowest part of any computation. And so when you're doing GPU computing, you have to be very careful not to accidentally or send data too much, right? A lot of times when you think about CPU computing, you think a lot about the number of operations that you're doing at a time. Like you think about the complexity of that operation, right? But when you think about GPU computing, because you're on this separate device with its own different memory, like registers and all this kind of stuff to deal with, when you deal with GPU computing, usually you're thinking not necessarily about the number of operations, that does matter, but also about the data flow, like where the data is, not only CPU, GPU, but also within different memory hierarchies in the GPU itself. And we'll talk about that with examples like in future lessons, but it is something you need to consider, right? Data flow is important here, and thinking about how that data is moving from one device to another is super important. So next, which was brought up in chat, a lot of simple operations, right? So this guy says, so it's basically doing, Casgame says, it's basically doing a function on a pixel, which means there are no sequential programming. Yes, so this is the thing. There's a couple things that are naturally bad on GPUs. One is iteration. Let's do iteration. 2 is going to be like traversal, let's say graph traversal. Anything, and 3, anything recursive. Interestingly enough, because graph traversal is so bad on GPUs, function pointers, because they actually call through like a call stack type of thing, are usually not allowed on GPUs, and you have to play tricks in order to do function pointers. But that's another issue for another day. When you think about GPU computing, you want to avoid loops, right? Because loops force a single core, a single GPU thread, as it's called, to do a lot more than it probably should be doing. Ideally, each GPU core is doing exactly one thing, and that one thing can be encapsulated with like a very simple function. And after that's done, you just kind of have all the pixels do their one thing and move on, right? And ideally, these one things don't talk to each other, which is why iteration is also kind of a little bit annoying, right? So like, for example, time stepping, like, you know, let's say we're dropping a ball from like this height to that height, like it's falling down, right? The act of simulating this ball movement from one point to another is difficult to do on the GPU, just because every time step requires a step before it in order to move forward, right? Other things that require iteration, like summation, naturally not super well suited for the GPU. Now, when we talk about summation, there are ways to reformulate the question to make it fast, which is why the very next lecture is going to be entirely focused on summation. But when it comes down to it, you kind of want to avoid iteration. You want to avoid recursion. In fact, it wasn't until like maybe 10 years ago now that recursion was even allowed on GPUs, right? Yeah, lots of things like here. And at the same time, when I talk about this, like again, the GPU is a separate device that's built to solve a lot of simple operations at the same time. This just means that we do have to think about parallelism. Like for example, if you do have to do some sort of time stepping, you have to make sure that all of the threads finish at a particular location. You have to synchronize them, add in what's called a barrier to stop all the threads so that they sync up at the right time. You need to think about how to deal with like atomic additions. That is like if you're adding one to like, if two cores are adding one to the same element in an array, you have to think about how to do that. This is all stuff that we'll talk about later. That I have specific issues or specific examples that we'll learn from for here. At this point, the data flow we care about, it's the bandwidth between CPU, GPU, memory, storage, but this delves into other stuff. Right, yeah, we'll talk about this. I have some good examples to talk about this in a bit. CPU was built during the time when procedural programming was king, right? Then, how do we sequence model? Was this sequential in nature? I don't actually know what we mean by sequence modeling at this point. I probably should, but I don't know what you mean by that. Also, gravity can't be done because forces would require communication between the GPUs. Well, this depends, right? If you can have all of your data on a single GPU, like for example, with an n-body simulation, you have like n bodies, all of them are like interacting with like different forces, right? So you have like F equals G M over R squared. As long as you have enough data on the GPU to hold all of your particles, that's fine. But as we start talking about like huge data sets and needing more than one GPU to hold that data, now it becomes a bit of a problem, right? And so there are like, in general, if you have the choice between using one GPU or two GPUs for something, I would always recommend finding a way to compress the data into a single GPU as opposed to using as many GPUs as possible. But clearly, supercomputers, high performance computers, they use many GPUs. That's what it is. So how long will this series be? I'm not entirely sure. I have 10 chapters intended to be written for the book. That might mean 10 different episodes for this series, but I'm not sure at this point. Why aren't GPUs directly on the motherboard like CPUs? That's a good question, because actually Apple Silicon does that. And this is one of the big, like, revolutionary changes, I guess you could say, that's happening in the industry right now. My cell phone does that. That's, you know, a lot of these new GPUs are actually that way. Oh, and iGPUs as well. And you can use iGPUs for this book, for this series as well. We'll talk about that in a bit. You'll be running demos on the stream, I hope? Yeah, I will. We'll be going through all of that as well. Okay, so we talked a lot about what GPUs are, what they're good at, what they're not good at. But let me talk about one thing that we didn't actually go talk about in depth yet, and that's the difference between compute and graphics. Okay, so when it comes to GPU computing, there's kind of two different camps, right? Graphics processing unit, that's the name of the game, right? And so you might argue that for the most part, the graphics processing unit should be pretty good at doing graphics, and it is, right? Obviously, it is. Unfortunately, the pipeline that we're using for this particular work is not the graphics pipeline. It's rather the compute pipeline. And as it is right now, though there are some trends to unify the graphics and compute APIs, when it comes down to it, these are two different things for the most part. For example, OpenCL is an open compute language was created by Kronos to do computation. Vulkan is a similar trend for graphics on the GPU, also developed by Kronos. Both of them compile down to the same lower level representation, yet that lower level representation cannot talk to each other, right? There's a fundamental disconnect between computation and graphics. So as we start talking about compute kernels, which is a specific function that's written for GPU computation, these are similar to compute shaders, which can be written for graphics pipelines. But there are a few distinctions between the rest of the workflow. For example, when you talk about the graphics pipeline, you talk about like creating a mesh, maybe importing a mesh, and then you can move all of these vertices around with what's called a vertex shader. This allows you to move the vertices around. And then you can shade all the triangles that are connected by this mesh with a fragment shader, right? You're shading the fragments. This is what I talked about earlier when I said we have a 1920 by 1080 screen, and that means you have 2 million pixels that you're shading. I brought up the term fragment shader because in principle, that's what would be doing the shading. And if you want to do like a ray tracing method, or we'll say ray marching, or something like this, typically what you'll do is you just draw a giant quad, a giant rectangle over your entire screen, and then you kind of do that ray tracing on each individual pixel in your fragment shader pipeline. You're using the fragment shader to do the ray tracing computation. Now, That's not entirely true nowadays because we have specific hardware to do ray tracing on modern GPUs, but that's how historically it was done. There's system on chip. It really kind of you to create such good content, and you get all the things CPU, iGPU, RAM in one. This is the worst part too, many standards and inconvenience. Yeah, let's talk about that. That's actually the very next thing I want to talk about. So the GPU works on the screen, 3D models. I was confused. So the GPU, this is, okay. There is something in the Vulkan land. There's something called a screen buffer, right? This is a specific number of pixels. It's like an array that you have to deal with. And when you modify the elements of this array, you are also changing the pixel content, right? Now, OpenCL, not Vulkan, does not have access to the frame buffer, right? And so what this means is as you are doing your computation, even if your computation is outputting an array with RGB values that should in principle be able to turn into a bunch of pixels to write onto screen, you then have to transfer it to a graphics API to do the real-time rendering. Now, if you don't care about real-time rendering, that's totally fine. In fact, a lot of the early ray tracing methods were done in OpenCL because we didn't care about real-time ray tracing at the point. And so when we didn't care about real-time ray tracing, it was totally okay to just like, render them all to some sort of image and save that file and take it a little bit slow, right? But when we start talking about real time, that's when we really need the graphics APIs. That's another good distinction between compute and graphics. Graphics, basically the main reason you want to use a graphics like centric API, like let's say OpenGL or Vulkan or even DirectX or something like this, is if you want to do these real-time rendering like game engines and this type of stuff. If you don't care about that, you might be able to do what's called a software rendering approach and do it all in a compute language, which I've done before. And in fact, one of the things that I'm doing right now for research involves creating my own software rendering approach for this type of stuff. Also, historically, the computers didn't use to be personal computers, but shared systems, and the users will only get text or terminal. Yeah, this is a totally fair statement. Like you used to have like render farms and stuff like this. Even early Pixar used to have like render farms that people would SSH into and get access to in that way. Okay, so there was a mention about here. This is the worst part, too many standards and inconvenience. Let's talk about that. Languages. This is where we start to get into, it's from Max. Yeah, that's fair. This is where we get into some difficulties when it comes to GPU computing. Whenever people ask me, like, how do you start programming? I always kind of say the same thing. I say, look, if you want to start programming, just start programming, right? And then they'll ask, well, they'll say, well, I want to make a game engine. And I tell them, well, if you want to make a game engine, then probably learn C# so you can interface with pre-existing game engines if you want to make a game. Or if you want to build an actual game engine, probably you want to like look at maybe Vulkan or OpenGL, though I wouldn't necessarily recommend that for a beginner. This type of stuff, right? Like when people want to program, the reason they want to program is because they want to create some sort of project. They want to do something. It could be research. It could be some software they want to develop. They want to do something with programming. It's usually rare that someone is programming for the sake of programming. They want to do something with that code, right? It's kind of like math. You don't just do math. You have like a clear goal as to what you're trying to do. You know what I mean? You know what I mean? So when it comes to GPU programming, we're in this really weird world where I cannot truly recommend any single programming language for GPU computation in 2025. Again, these videos are made in 2025, so if you're watching this in 2026, 7, 8, 9, maybe in the future there is a perfect language for GPU computation, but right now I don't necessarily have one. And the reason is that the languages are very hardware dependent right now. This is something that's kind of hard to describe. So let's imagine you buy a CPU, right? And you buy an AMD CPU, right? Imagine if you're now no longer able to use Rust, specifically because you chose to use an AMD CPU, and it's mainly meant for Intel CPUs. You know what I mean? This is kind of the situation we have. Obviously, you can use Julia, you can use Rust, you can use C, you can use pretty much any programming language on pretty much any CPU, but that is not true for GPUs. If you get an AMD GPU, you can't use CUDA. If you have an NVIDIA GPU, you can't use Metal. If you have Apple Silicon, you can use neither CUDA or HIP, which is what's used for AMD GPU, right? And so depending on your hardware, you have to choose a language that works for your particular system. So let's talk about languages, right? And I've put these into categories of languages that I've used, languages that I know about, and languages that I cannot comment on for various reasons. So I started off my GPU life doing CUDA. This was way back in, let's say, 2014, maybe even earlier. No, 2014 is probably about when I started here. So about 10 years ago, right? CUDA is a fantastic programming language. I would recommend it for people who have NVIDIA GPUs. It's pretty good. It is essentially an extension to C that allows for you to write what are called kernels, they're GPU functions, to allow you to program what each individual core on your GPU is doing, right? Now, let's say you don't have an NVIDIA GPU. Well, then you want to use OpenCL. So historically, if you had an AMD GPU, okay, you don't necessarily have to use OpenCL, but let's talk about the advantage of using OpenCL. So historically, if you had an AMD GPU, which meant you could not use CUDA, you would want some other compute language. And that other compute language, historically, has always been OpenCL. OpenCL stands for the Open Compute Language. What this means is if you write code for OpenCL, it will work for any GPU, right? In fact, I pulled out my phone earlier. You can run OpenCL on this. Like, it will run on your phone. That's pretty cool, right? So it will run on AMD, it'll run on NVIDIA, it will run on Intel, it will run on your phone, it will run on Macs even, though it's technically deprecated on Mac, so I don't necessarily recommend that. It'll run on anything, right? And that's really powerful. It means that if you write code in OpenCL, you can guarantee it will probably run on almost anything. That is also true for like Vulkan, for example, but that's a graphics API and it comes with its own can of worms, which we talked about before. So if you have a language that only works on NVIDIA GPUs and another language that can work on anything, right? You would expect the language that could work on anything, right? The language that could work on any piece of hardware would win out in this war, right? You'd expect that OpenCL would be the de facto king of GPU computing because it just is more capable. It can do more things. But that's not necessarily the world that we live in today. Unfortunately, the tooling for OpenCL is just a little bit more difficult than the tooling for CUDA. There are actually some workflows where OpenCL is actually easier to use than it is for CUDA, and I have a couple workflows like that I may or may not mention in this book series, and in this lecture series. But for the most part, OpenCL's tooling is considered distinctly worse than CUDA's, right? And because of that, CUDA kind of took over, to the point that, you know, when we talk about NVIDIA, yeah, they make GPUs. GPUs are for gamers, but NVIDIA's primary business model right now is not necessarily courting gamers. It's courting people who are using the GPUs for computation. CUDA is, I think at this point, unless it's changed recently because of some, you know, DeepSeek nonsense is happening in the real world, for the most part, CUDA's primary, NVIDIA's primary, shtick is developing GPUs for computation. And CUDA is like the number one reason why NVIDIA is one of the richest companies, probably in the history of the world. I don't know how true that is, but they're an incredibly rich company, and it is because of CUDA, right? They made CUDA the de facto, the default programming language for GPU computation, and because of that, everyone buys NVIDIA GPUs because otherwise they can't use CUDA. And it's this cyclical argument where, yes, technically you could write code in OpenCL, technically it is pretty much the same speed, technically it is better because you can run it on any hardware, but it's not CUDA, and CUDA is where everyone else is, and that's the world that we live in right now. So when we talk about GPU computation, it's almost impossible to ignore what I call the big green elephant in the room, and that is NVIDIA and their programming language CUDA, because they are the kind of bullies in the sphere. They're the ones that are playing market. How do I put this nicely? They're the ones that are pushing the development of GPU computing and GPUs in general more than any other company. Right? That's what I want to say. Let's keep going here. Are these basically assembly languages? No, but that's a good question. So let's talk about the computation pipeline really quick. So we'll start with a programming language, right? So let's just go through the Julia stack. So we have Julia, right? Julia then goes down to LLVM. LLVM boils down to machine code, right? When we talk about GPUs, it's kind of the same thing, right? So Julia then goes through CUDA.jl, which then goes to an LLVM-like language called NVPTX, which then goes down to GPU machine code. Now, when we talk about this level, LLVM and NVPTX level, I'm going into way more detail than I wanted to at this point, but let's just talk about it. The transformation between this level of code, this lower level intrinsic level of code, to the device code is actually very dependent on not only your hardware, but also the driver that your hardware is running. Right. This is why if you've compiled Vulkan shaders, you sometimes have to compile Vulkan shaders again and again and again, even for the same game, even after you've already compiled it the day before. And this could be because you've changed your GPU driver somewhere under the hood, right? And this causes the machine code to be developed slightly differently from this lower level interpretation, right? And so when we're talking about where these languages sit, they are about at the same level as Julia or C or these other languages. It's just slightly lower level than that. And in my mind, in terms of parallel computation, it's actually easier to use CUDA.jl than it is to use like threads.atthreads, which is a parallel implementation for Julia. It just depends on who you're asking. So in terms of high and low level, you can kind of assume them to be at roughly an equal level to the programming language that you're used to, roughly. You'll see some jank here and there, but roughly the same level. And these then compile down to some lower level interpretation than machine code. So it's not assembly code, right? Will OpenCL run within some limitations? Yeah, so the limitations for OpenCL are usually that it has roughly a 10% performance penalty versus NVIDIA, versus CUDA. This isn't always true, but roughly 10% is what people get in most contexts. But the advantage of OpenCL is that you can do many more tricks with metaprogramming with OpenCL than you can with CUDA, to the point that if you end up having to do metaprogramming on GPU kernels, it almost doesn't make sense to use CUDA because in OpenCL, they're just strings, and you can manipulate your strings as much as you want. They're not compiled in the same way. Rather, the kernels are not compiled until runtime for OpenCL, and that gives you the advantage of allowing the user to manipulate their own kernels in a way they can't do with CUDA. And that's a big advantage for a lot of different people. Echo, my prompt shrunk. I don't know what happened there. What do we have? NVIDIA is selling shovels for gold diggers. Will there be tests? CUDA ecosystem. I'm trying to catch up on chat. NVIDIA, like, I don't want to sit here and say NVIDIA is evil. I don't necessarily think that, I don't want to get into the politics here. I heard you like languages, so I put a language in your language in a language. That's what this is, though. Slightly above machine code, pretty low. I was just thinking about how only certain chips and certain languages correspond. Yeah, the truth is that there are some languages, like for example, Mojo and Julia, that allow you to write, and even OpenCL. These are called performance portable languages. So these are languages that give you an abstraction layer that allows you to write code that can then can be ported onto any hardware. That's what they do. And when we talk about performance portable languages, OpenCL is my favorite. And Julia, those are my two favorites. They're probably equal in my book. But historically, the reason you can't run CUDA on other on other hardware is just because of bickering between like AMD GPU and NVIDIA in terms of company dynamics. It's not really for any logical reason in my mind. And imagine NVIDIA being them. Will limit your access to CUDA codes in some way or short. I have older NVIDIA cards and can't get them running CUDA. Drivers are not there anymore. Yeah, that's fair. It's a weird world. I'm looking at the chat down here. I'll go ahead and catch up. Let me go. I've got lots of chat to catch up on. Anything is evil. Now we can move and get stuff done. Yeah. My initial view of the AI stuff was, why would the chip used matter, as the algorithm is the algorithm? But it's not that way. That is true. Right now, unfortunately, we live in a world where the language that you choose is tied to hardware. In an ideal world, this would not be the case, but OpenCL lost the battle. And because they lost the battle, we now have a huge fragmentation in GPU ecosystems. CUDA might be fine for research, but you can't release a game or any other consumer app that requires NVIDIA, so we need something better. Yep, I agree with this. We'll talk about that in just a second. Let me go to catch up on YouTube chat as well. Triton. So I don't know much about Triton. That's down here, number 4. The one language that chat is always talking about. They always bring up Triton, a few other languages as well. This is in the languages I can't comment on. They got 2 moats, CUDA and InfiniBand networking. I can't wait for the future of open source, open ISA GPUs. I hope. I can only hope that the future is better performance portable languages. That makes sense. I keep updating my GPU drivers, and that's why SteamVR keeps updating Vulkan shaders. Putting language in a language putting a language in a language sounds like a Toadapond video. I don't know who that is. Same driver is also a pain. Yeah, so look, long story short, this entire process is way more complicated than it needs to be. And going back to the statement I said before, when people ask me, how do I start programming, right? I can usually give them some examples, right? Again, if they want to do app development, web app development, I'll be like, I don't know, maybe JavaScript. If they want to do, I don't know, systems engineering, I'll say Rust. I can give them a language, and I can say, this is the language you should probably start with, not necessarily the language you're going to end with, but the language you should probably start with. And after starting with this, you can then figure out the ins and outs of the trade of what you want to do in the end. You learn more about your project, and as you start learning more about your project, then you can switch over to another language, right? Unfortunately, right now, I can't recommend CUDA because, unfortunately, you just can't use CUDA if you don't have an NVIDIA GPU. And my assumption is a lot of people here in this chat probably don't have an NVIDIA GPU available, right? You can't. I'm not going to do OpenCL because there's too much boilerplate. It's just kind of too annoying. I personally like it, but I understand other people might not. I'm not going to use OpenGL because it's a graphics API, and like I said, we really can't use the majority of a graphics API for this particular lecture series. I'm talking about GPU computation, not GPU for graphics. That's what this is. What about SPIR-V? What a good question. What a good question. Hey, thank you so much for asking that question. I feel like I planted that question. So SPIR-V, what my favorite. SPIR-V is my favorite. So let's talk about this. So there's Vulkan. It compiles down to SPIR-V. Now, let me tell you something. OpenCL also compiles down to SPIR-V. Now, what is SPIR-V? SPIR-V is a LLVM-like dialect. So it sits on this layer. After your initial programming language and your writing of your code, it compiles down to this lower level representation and then to machine code, right? Vulkan compiles down to SPIR-V. Vulkan is a graphics API. OpenCL compiles down to SPIR-V. OpenCL is a compute API. And you might think to yourself, ooh, hey, both of these languages compile down to the same lower level representation. So you must, in some way, because they both compile down to SPIR-V, they must talk to each other. But there's a problem here. Even though they're both called SPIR-V, they actually don't talk to each other. And so there isn't a world where you can compile down a compute kernel in OpenCL and use that as a compute shader in Vulkan. It would be nice if we could, but we can't. You could argue, it's insane to me that we can't, because the initial concept of SPIR-V was to unify compute and graphics together, but unfortunately, that's just not the world we live in today. The reason has to do with function pointers. OpenCL 2.1 allowed for people to use function pointers on in GPU kernels. And Vulkan would never allow for that except for in the ray tracing API. And so at a fundamental level, there's like it's not just function pointers, but stuff like that is what kind of breaks the connection between the two of them, such that you just can't use them together. There's a lot of just historical reasons as to why these are separate. As I remember, every GPU can't run CUDA. Yeah, so CUDA can only run on NVIDIA GPUs. OpenMP or OpenACC, again, I have never used OpenACC, but I'd put them in the same level as Cocos and Sickle. We'll talk about these in a bit. So we talked a bit about CUDA, we talked a bit about OpenCL, we talked about OpenGL being a graphics API not suitable for this, as well as Vulkan being a graphics API not suitable for this. And just for the record, the amount of boilerplate, like unnecessary excess code that you have to write down for OpenCL and OpenGL, it's just too much. And Vulkan, way too much for this work. We could just stick to the compute shader pipeline in Vulkan. That's fine. And there is good reason to do that. There's a few packages that, through using Vulkan, actually get better performance than in CUDA, VKFFT being one of them. But for the most part, look, we need to stick to compute languages. So what other compute languages could we use? Well, we could use Metal. That's like a hybrid compute graphics API for specifically Apple Silicon. Let's do Apple Silicon. We could use RockM or HIP. This is going to be the same, but for AMD. We could use one API. I think you can technically use this on any GPU, but it's mainly for Intel GPUs. So for the same reason as to why we can't use CUDA, we probably can't use any of these languages either. So I'm just going to go ahead and cross off CUDA, OpenCL, OpenGL, Metal, one API, and RockM. Okay. So let's talk about other languages. Let's talk about performance portable languages, right? Because the core reason I've knocked most of these off the list as to languages we cannot use for this work is because they're not able to be used on any GPU, and I don't know what GPU you're going to be running on. Right, so let's talk about performance portable languages. We've got Mojo, we've got Futhark, we've got Bend. I've never used these languages, I can't really comment on them. We've got Sickle and we've got Cocos. The problem with these is they don't allow you to write, they do allow you to write GPU functions, but they're not as extensible as I would like. And that leaves the only language that I can actually like use for this work, which is Julia. Like, on the one hand, I need to talk about Julia, right? Because, you know, I mentioned at the start, I've been working the Julia lab at MIT for the past, 5 years now. So it is the language I know most. And when it comes to learning GPU concepts, I've said time and time again that Julia has the best GPU ecosystem in the business. It's so much easier to use than CUDA. It's so much easier to get the installation done. It has multiple different abstractions that you can use for doing computation with. It's just, there's a lot of like, I know I'm biased here, but I truly believe, and I hope that after you guys go through this lecture series, you will also understand at least my point of view when I say that the GPU ecosystem in Julia is genuinely the only reason to use the language in 2025. That's it. And plus, it's relatively simple to use, like Python, like Cas Games is saying. And so even if you don't know C, there's not so much C that we have to interface with here. Basically none, right? We can do everything in Julia. It should be high level. We should be able to teach all the concepts you need for GPU programming. And then as you start moving into like using these concepts in a real workflow, then you switch to the language of choice. You can switch to CUDA, you can switch to OpenCL, it doesn't matter. But the point is we need to teach the concepts. And to teach the concepts, I think Julia is the best for this. I did have a huge debate in my head between Julia and OpenCL, but I landed on Julia in part because of my own biases, but also because Julia is the only language that is both performance portable. It's not deprecated on Mac, just for the record. You can use Julia on Apple Silicon just fine. And it also has multiple abstractions. You have not only the ability to write your own GPU kernels, which will be just as fast as vendor-specific languages like CUDA, but you can also use broadcasting, which is a very simple way to write code out in like a very like algebraic way that will turn into just as fast kernels, again, like CUDA performant level kernels. And you also have loop vectorization, which is what's used in SYCL and Cocoa. So you have the ability to use any abstraction in Julia, whereas you don't necessarily have that in other languages. See, I'm biased, but this is where I'm at. Is this an ad now? It's a bit of an ad, unfortunately. I did a lot. I thought a lot about this, and I really did. I was going to focus on OpenCL instead, but at the end of the day, as I started writing the book, I found that Julia was just so much better at showing off the concepts that I'm trying to teach. That was it. That was the reason. I missed some chat up here. We need to wrap all those languages into one single library and rule them all. That's actually what we do in Julia. So Julia has a CUDA.jl backend, an AMD GPU backend, a Metal backend, a OneAPI backend. And so what we do is we just have Julia sit on top of them all, and then they literally go back down to like the lower level representation for those languages, right? That's what we do. It's one language that ends up going down into each vendor's specific language. In that way, it's similar to Mojo. Mojo has like a mid-level intermediate representation above the LLVM. Man, I'm really going into detail here I didn't want to go into. Point is, it allows you to create the lower level representations of all the vendor specific languages without you necessarily having to dive into those vendor specific languages themselves. Let's see, these things branch out from source. Julia helps you solve your problems, therefore you can start using it. Exactly, that's where we're at right now. You can do stuff with Julia, figure out how it works, and then move on to a more like a real programming language for whatever you want. That's what it is. Do you still have indents for loops? You don't have to indent for loops. Where's audio? So Vulkan does compute. Yeah, so just to finish up the discussion on Vulkan and OpenCL, Vulkan does have compute shaders, but they're different than compute kernels in OpenCL. Is using an off-screen buffer a reasonable alternative to compute, or is there some bottleneck I'm not aware of? In principle, yeah. You can. This is what they used to do back in the day. They used to use fragment shaders to do computation, and that's what people did. So it's kind of the you're hitting the right notes. Real programming language like machine code. Look, we're not doing. No one can do machine code. It's not even theoretically possible. Okay, so with that said, I think we can go ahead and get started and talk about different abstractions that you can use on the GPU. So new page before. There are going to be 3 different abstractions that we're going to talk about in this work. The first is going to be broadcasting. The second is going to be kernels, which I've talked about a lot. They're like GPU specific functions. And third is going to be loop vectorization. But I'm probably not as vectorization. But I'm probably not going to talk about loop vectorization too much, except as a warning to people who want to write GPU code by using loops. We'll talk about that as we get to it. But suffice to say, I'm not a particularly fond of people just taking pre-existing for loops and parallelizing them on the GPU. It doesn't actually solve the complexity issues that you have when you're moving to the GPU from CPU programming, and it really only exists as a crutch for people who don't actually want to learn like good, I would say, abstractions for the GPU. That's my personal opinion. We'll talk about that more as we get to it, because I'm sure some people are going to be very upset with that statement that I just said, but that's my personal opinion. Any opinion on GPU computing in Mathematica? Can you do it in Mathematica? Mathematica is like very much it's focusing on algebraic systems, which are really bad on GPUs. So I'm not entirely sure if that's what you want to do. It's always good to sprinkle in some flashy demos to keep the interest up. Yeah, we have some demos. I have a demo today. Do GPU compilers do fancy tricks like CPU ones? Yeah, they do. It's a lot of them. The advantage of working on these lower level like languages, or lower level intermediate representations, is that you can do like loop unrolling, and a lot of this kind of stuff just naturally. Like LLVM will do that for you. You know what I mean? And so that's why people standardize on LLVMs for V, this type of stuff, so that the compiler can do these kind of tricks. So let's go. Let's go ahead and start by downloading Julia. Fun fact about Julia. Just Google Julia Lang. You'll get the Julia programming language, but you also get a picture of Julia Lang on the side here, unrelated to the Julia programming language. I don't even know who that is, to be honest. But the Julia language has been constantly fighting to get Julia Lang removed from the side view when people Google Julia Lang. From, you know what I'm trying to say, like, because now people have an association between these two and they're not associated at all. Anyway, it doesn't really matter. I'm like rambling about stuff that doesn't matter. So here's what you do to install Julia. You go to download, and then essentially you just run this command. So I'm just going to run this command. That's what I'm going to do. And we're going to do Julia installation together. So let's go over here. I'm going to open up a giant terminal for today, guys. Much different than the terminals I typically open up. So we're going to make a big old terminal for today. So that's maybe too big. That's the size I want. All right. 1 second. There we go. And now we're going to CD into projects, GPU, and I'm going to create make directory GPU handbook. CD GPU handbook. Good. So we're just going to grab this command. We're going to paste it in here, and we're going to go. Now, someone asked about Windows. Proceed with installation. And I hope it works. I'm trying to do this on stream live in front of you guys. I just assumed it would work. But while it's doing its download and all that kind of stuff, I do want to mention, yes, you can do it for Windows. Here, so you can do the Windows as well. But you do have to run it in the command prompt for this. If you don't want to do it that way, you have the binaries that you can install here. Windows with an installer, portable, Mac OS, all this kind of stuff, right? Piping the output of a curl command right into the SSH. Yeah, I'm not necessarily arguing this is the best thing to do. I just trust that that site. What did I do? Do you want to proceed with installation? I might have messed up. Downloading which shell. So if I run Julia now, what's it going to run? This runs 1.10.2. That wasn't what I wanted to do. Oh no, that was not what I wanted to do at all. Let me do something really quick. I really messed up, didn't I? So let me go into... You don't see this. Oh, it's Julia. All right. So what this will do, let me show it to you guys now. I just have to show you my bash RC. It will add something to your bash RC file. Oh, 1 second. I have to show it to you. I didn't mean to do this. Okay, it's okay. We'll talk about it now. So it adds something to your bash RC file, which is like Julia up initialized, context within this blocker managed by Julia up, and then we have this here. Now, what I did not mean to install Julia up. This was actually not something I meant to do. What I should have done is just downloaded the tarball and gone from there. So I don't actually want this. Which means I do have to update the text in my book to reflect the fact that I don't actually want that. Yeah, I don't actually want that. So I think what I'm going to do is I'm just going to delete all this from my bash RC file. And I'm going to, yeah, I'm just going to delete all this from my bash RC file and we're going to go from there. DG, write and quit. And we're going to instead download the tarball because that's what I know how to do. And that's what I should have recommended in the book. So that is something I need to update. So we're going to grab the 64 glibc here. We're going to grab that bad boy. Bad boy. This is me learning on the go. It's okay. I haven't done a Julia installation in a long time. I usually just grab the tarball and go. So we're going to grab this and we're going to build it. Oh, that's what I get for trying to do a lecture series without properly like going through everything beforehand. But that's okay. So we're going to go over here. We're going to CP downloads Julia 1.1 here. And I'm going to do tar xvzf Julia here. And now we have Julia available. Okay, so for the record, just to wrap up what we just did there, because I obviously should have tested this beforehand. Okay, so here's what's happening. what I did is I installed Julia via Julia up, okay? And what this tried to do is, so it installs the Julia up installation manager, which will automatically install Julia and keep it up to date. The command Julia up is also installed to install different Julia versions. See Julia up help. So I think if I do Julia up, no, I don't. So I think if I open up a new terminal and then type Julia up, no, okay, I don't know what happened to Julia up, to be honest. I don't know where that went. That's something I probably should have. Well, I learned a lesson today. We should probably not just grab random commands from the internet and run them. I just kind of trusted that this would do what I thought it would do, and it did not. Just a preview. Do you have any AI neural network demos in the course? I do not, because it's a lecture series on GPU computing, and to be honest, I have no interest in AI, just in general. And also, like, I don't want a chapter talking about AI, because then I could write 3, 4, 5 chapters on AI. You know what I mean? Like, it ends up becoming it's kind of too much for the scope of the book. But if people really want, that, I could consider doing that. So let me just kind of read through this and make sure I understand what just happened. So it looks like you're using Unix Linux. So once installed, Julia will be available via the command line interface. This will install Julia up installation manager, which will automatically install Julia and keep it up to date. So I think what happened, if I do cd Julia, there should be a Julia and then a Julia up. Okay. ls bin. Yeah. Okay. So what happened was, when I did the Julia up version, it created a separate installation of Julia in my home directory under the .julia up directory .julia up -bin, right? And then it gave me 2 different Julia binaries to run. It had Julia in the command line that I could run, and then it also says Julia up to update Julia in such a way. And then it added the command line arguments to my bash RC so that every time I open up a terminal, I can then use Julia. So if you guys did the Julia up version, what you might have to do is run the command source /bash RC in order to run the Julia command. That's what you might need to do. Anyway, projects, GPU handbook. Layouts of preview. Let's see. Blind speedrun of boot looping via Julia. Yeah, I messed up a little bit there. Did you title the book? The title of the book right now is the GPU Kernel Handbook. I could say like with Julia or something, but I don't really think that's necessary in this case, because the goal is not necessarily that I'm focusing on Julia so much. It's more that I'm focusing on teaching GPU concepts, and it just happens that Julia is the best language for that. Joke's on me for running 0.9 speed. Oh, you're running, like, you're not watching it as fast as you could. That's fine. Okay, so just to clear up what just happened, there are 2 ways to install Julia. Installation process number 1, you do this command here, or this command for Windows, right? This will install Julia up and Julia. If you do it this way, you have to make sure that you source the bash RC file using this command, and then you should have Julia naturally installed. The other way to do it is to download the specific binary and to install that, and then you'll have a local version of that available. So if I do an ls here, I have Julia -1.11.3. So cd Julia 1.11.3, ls here, cd into bin, ls here, and then I have Julia here. So if I do pwd, you'll see that I'm in home, layouts, projects, GPU, DPU handbook, Julia -1.113 bin. And if I run /Julia, I now have the shell available. Okay. Are you restricted to graphics or some sort of general parallel programming? So it's not necessarily graphics, because we're using Julia for this, so that if you do write your code in kernel abstractions, you can also run parallel CPU programming. And I mentioned that in the book. If you guys do not have a GPU available, that is totally fine. It's not actually a big deal. You can also do all of the code in this book, everything in this book, on your CPU. And then when you get a GPU, the code should just run on a GPU. That's also another big advantage of using Julia for this. Let's see. I use it sometimes for testing without having any issues. You can try DistroBox and start from a blank slate. To an install Julia binary. Oh, that's the other thing you could do. You could also do sudo pacman -ss. How do you search again? SS, right? Julia. And this should give you all of the different Julia versions available. So you could install it from your package manager if you're running on Linux. There's a bunch of different ways to get it installed. For a non-Arch user like Ubuntu, you could do sudo apt-get search Julia. I'm sure there's something available in Julia on your particular language. Okay, so now we're going on to the fun part. Okay, so I have the Julia language installed. right? Now let's start talking about how to actually start GPU computing. The first step is to identify what hardware you have on your system. Now, there are a bunch of different ways to do this, and I'm going to go ahead and link the introduction book here. So all the ways to GPU. Again, I'm going to post this link here, and I'm going to post it here. Go down in the installation section and figuring out what hardware you have. So depending on your operating system, there could be a variety of different hardware available for you to use. If you're on Windows, go to the device manager, look under display adapters, and you should be able to find the device that you're working on, or find a GPU that is available there. If you're running a Mac, check to make sure you're running an M1, M2, M3 Mac, one of the latest versions that are running Apple Silicon. If you're using that, then you should be able to use Metal, which is a package specifically for GPU computation on Mac. If you're doing Linux, there's actually a bunch of different ways to figure out your hardware. I usually use lspci grep VGA, but I'll also show a bunch of different commands as well. So this is what I typically use. I'm not saying it's the best thing to do, but I usually do this, and it says I have two AMD compatible controllers. So I've got a 6700 XT, which is the one I usually use, and then this one, which I don't know what it is. I've never used it before, but it also shows up when I do OpenCL and stuff like that. What happens if you install it via the package manager? Nothing really. It's just that sometimes package managers bundle some additional things in. So the Arch Julia binary installed via the package manager somehow is different than the binary you get from the website, and it's not very clear what the difference is, but I've actually had issues with the Julia binary installed from the package manager, whereas I haven't had a problem with the ones installed from the website. So every once in a while there's a difference, but usually it's fine. Let's keep focus tight, only GPU. That is what I'm focusing on. It's just, it happens to be that you can also do this on the CPU. Using Nix dev shells would also work without having to install it. It'd be reproducible across the machines too. This is true too. A lot of people have been using Nix, or not a lot of people, but one of the people who has reviewed this chapter so far was using Nix, and they had different ways to do everything. And that's fine. If you're using Nix, it's fine. Just do what you feel is best for your operating system. I trust that you know what you're doing. So another command you could do in Linux is lshow cdisplay. I don't have lshow installed, but you could technically do this. But the other one that people showed me was more interesting, actually. So you can actually open up Firefox and go to about, what is it? It's about add-ons? No, about support. And if you go to about support on Firefox, I think anyone can do this, but it should be able to tell you what you have available in terms of hardware. Let me see if I can find it. AMD. So WebGPL driver renderer AMD, right? Let's see if it's available elsewhere. Let's do AMD. Okay, lots of AMDs here because everything's AMD. But in principle, you go to the WebGPL driver and you should be able to find what you're running. So about support. Yeah, so this is another way to do it that I just learned about the other day. 1 second, I have to cough. Okay, so hopefully that's enough information to get you guys started. The truth is, again, like I said before, the GPU computing ecosystem in general it's incredibly split and divided. It's very difficult to figure out what you have to do to get started, right? And so the first thing you have to do is identify what hardware you have on your machine, which, again, you didn't have to, any of the stuff that I just showed you, lspci, grep VGA, lshow, Firefox, if you just knew what card you put into your machine because you built it yourself, or you're running an Apple Silicon device, so you know it has to be Apple Silicon, or you bought your own machine and, your GPU, you knew it was an NVIDIA GPU, you've already done this, right? All I was doing to show you right now, all I was doing right now was just to allow you to verify what hardware you have on your machine. Now, because we're using Julia, everything that we're doing here is performance portable. That is to say, you can run whatever code that you're running. You can write, the code you're writing in Julia can run anywhere. That's what I wanted to say. So it's not going to be an issue, but if you were not using Julia or OpenCL or something like that, then the determination of your hardware would be very important, right? So now we have, not only have we installed Julia, but we've also gone through and we have figured out what hardware we have available. For me, it's all AMD. That's fine. For other people, it might be all NVIDIA. That's fine. Other people might have Apple. That's fine. Maybe there's one person in the audience who has Intel. That's also fine. It's totally up to you. AMD RX 580 after I smoked the 480. I've done that. I've destroyed multiple GPUs before. A closer replacement I could find. Most package managers do a terrible job of handling different languages, ecosystems. Python and Haskell are usually poorly handled, and it's the reason why many languages have Julia up, Rust up, GC up. Yeah, that's fair. Do what the language says, not what your OS is usually a good advice. Yeah, that's true. If somebody wants to get into GPU programming, they probably know what GPU they have. That's true too. I just covering all the bases here. All right, we've rambled too much about this. Let's go ahead and run /Julia, which will open up our Julia shell. Now we have Julia available. Now here's where I need to talk about something about Julia that is maybe a little bit different than other programming languages. So Julia has a concept known as type inference, right? Okay, most languages have type inference if you're running a dynamic language. But the way in which Julia works is it does not compile a function until it knows statically what the types are. So for example, if we run a function of, let's say, x, a, b, right? It doesn't matter what it is. Let's just say f of x, okay? And we say it's going to be equal to x plus 2, right? This is a generic function. We don't know what the type of x is. But once we run f on 1.0, well, now it knows that it needs to compile a version of f to run on floats, right? The reason this is important is because we are going to be leveraging something called multiple dispatch for this work. That is to say, we're going to be running code, and we're going to be dispatching that code based on the array type. So we could do f of a, which is of some type abstract array, right? And this will do something with a, right? I don't know what it's going to be, but it's going to do something with a. And because of this, it's important to not only know necessarily what package you're installing, but which array type is useful for your specific hardware. So let me just explain. I'm using an AMD GPU. So what I have to do is I have to install AMD GPU, and I have to use the rock array type for this work. If you don't know what array type to use, just go down here, right? So if you have a parallel CPU available, don't worry, you don't have to install a package. You're just going to be using the classic array type. If you have an NVIDIA GPU, you'll use CUDA package and the CU array type. If you're using AMD GPU, it's AMD GPU and rock array. Intel GPU is one API and one array. And Apple Silicon is metal and metal array, spelled MTL array. There's another restriction for Apple Silicon in that you can only do float 32 support. It doesn't have float 64 support. And by default, numbers are float 64 in Julia, so that's something to keep in mind. But I also mentioned that in the chapter as like something to just talk about. So first things first, we need to go into the package manager and install the appropriate package. So to do this, type this key. It is the end bracket key, okay? This will open up a package manager here. So again, it is this key, the one that the end bracket key. Type that in, and you open up the package manager. Now you can do add AMD GPU in my case, and again in your case, depending on your hardware, this might not be AMD GPU. It might be CUDA, it might be metal, it might be one API. I don't know what it's going to be, but you know, for me, it's AMD GPU, so I'm going to add AMD GPU. Now, if you don't want to use the package manager in this way, that's also totally fine. I'll show you how to do it without the package manager in just a second by using the package. But let me just go ahead and get through the installation here first. And once this is installed, we've already done, like, in my opinion, one of the most annoying bits of GPU computing. That is getting everything installed, figuring out the drivers, all that kind of stuff. Julia just does it for you. It's a bit magic, to be honest, but you know, it's good that I don't have to think about it. Side question, is it recommended to compile Julia to make use of AVX 512 or other less common languages? That seems not really portable. Is there no automatic inference for the array type? So this is a question, right? The reason we dispatch on the array type is because, in principle, you could have multiple different GPUs available, right? So you could have both an AMD GPU and a CUDA GPU, right? The only thing we know is where that data sits, right? It sits on the CUDA GPU, it sits on the AMD GPU, it sits on the CPU. That's the only thing we know, right? And because that's the only thing we know, we can dispatch off of that, right? But if, you know, like for example, if you have some data on a CUDA GPU and some data on an AMD GPU, I mean, we can't do anything. We can't, like, what do you want us to do? Do you want us to transfer the data back and forth? The primary thing that people care about for GPU computing is where the data lives, right? Not only does it live on this GPU or the CPU or that kind of stuff, but also where it lives in GPU memory. Like, that's what people care about. And so we have to make that explicit, the discussion of where the memory exists. And basically, anytime I've seen people try to make this implicit, as in, like, they try to hide this fact away from the user and they try to make it, like, so that people don't have to think about where the data exists, exists, it ends up causing more complication down the line as you start getting into the more generic programming models. And so we made the conscious choice to say, look, the only thing you have to worry about is where the data exists. And to figure out where the data exists, you just put it into this array type, and we dispatch off the type. Julia's UX is great. I'm jealous. Having package installation in the REPL is really nice. It's really nice. I really enjoy that part. So if you did not want to press this button, again, the close bracket button, or you couldn't figure out how to get that to work, that's also okay. Type in using pkg, and now do pkg.add, and then quotes AMD GPU. And this will do the same thing. And in general, all the commands that we use within the package manager, you can just use package dot and the command, and it'll work as well. Okay, so now we have AMD GPU installed. So we're going to using AMD GPU. There we go. It's used. And now I'm going to create an array. I'm going to create an array, and it's going to be equal to zeros of, let's say, I don't know, 10, 10. All right. Now, this is another one of those things that's maybe a little bit different than if you were writing code in C. In C, you want to allocate the data, and then you want to fill the data with zeros. You could also use calloc to make sure it's all zeros to start. But usually what you do, or what I'm used to doing, is you do a an malloc step, malloc, and then you do, you fill it with data afterwards. This is important because if I type in B is going to be equal to rock array of A, this is going to do two things, and it's kind of subtle as to what the two things are. One, it is going to allocate data on my GPU, and two, it's going to send data from the CPU that is in the array A and move it to that location in memory for B, which is now on the AMD GPU. Right. So it's a little bit tricky. And the only reason I bring it up is because, again, when we talk about GPU computation, the most expensive part is memory management, right? And it is a little bit annoying that the allocation step and the transfer step kind of happen implicitly with this. I kind of wish it was more explicit. But you also notice something there. Let me just show you again something that was a little tricky that you might not have seen. So we do using AMD GPU. Now I'm going to do A is equal to zeros of 10. And I'm going to do something. I'm going to say at time, B is going to be equal to rock array of A. Okay, that took 1.8 seconds. 1.18 seconds. You're telling me it takes 1.18 seconds to create 100 numbers? That's not exactly true. Okay, and this is something that I need to bring up about Julia. Though we have been doing the best we can to get the compilation time down for Julia, because it is a dynamic language that doesn't do the compilation until it can statically know the types, when you run a command for the first time, you're going to get a slowdown, right? Because that slowdown is the compilation of the entire pipeline. So if you read this, it says 3.7 million allocations, 2.44% grab-rich collection time, and then 87.53% compilation time. Right, so almost all of that time, that 1.18 seconds, was spent compiling the code that will eventually run on the GPU. And this brings up an unfortunate truth for GPU computing in Julia. Yes, Julia is fast, and it can get the performance that you would expect from CUDA, ROCm, HIP, whatever. But you have to do the timing on the second run, because if I do this again, now it's like insanely fast, 0.00152 seconds. And in fact, you could argue that this at time command is not exactly correct because it's timing from the CPU, whereas you want to time from the GPU. And this is why all the vendors have an AMD GPU .at time command, or metal.at time command, or one API at time command to time it from the GPU's perspective as well. Again, this is all just kind of caveats to talk about when we're talking about Julia. Yes, it is performance portable. You get the performance you want, but in that portability and in the the act of making Julia run on GPUs, we do incur a large compilation cost. So that's just something that you have to keep in mind. Let's see. Networking is considered even slower between racks. Is there a way to make this visible, as in step transferring array similar to the time macro, which tells you how much was allocated? Transfer to from accelerator. Is there a precompiled command? Yeah, you could technically do a you can do precompile equals false, true. When you run Julia, you can run it such that it ignores precompilation. It just assumes precompilation has already happened. I don't remember what the command is. I think it's like Julia precompile false or precompile true. I don't remember, but it is possible to do this. Julia's UX is great. Okay, so in terms of figuring out like what's being allocated and when, this is the difference between running AMD GPU at time. This will tell you the number of allocations. Yeah, let's just run this one more time. And also I'll show you something else here. If you want to run Julia in multi-threaded mode, you can do -T12, and this will run Julia with 12 threads. These are CPU threads, so it's not related to GPU programming, but I bring that up just to say that as you're running and launching the Julia command, you can add in different command line arguments. So this is where you'd add in that precompile false. So using AMD GPU, again, A is going to be equal to zeros, and then we do B is equal to this, and I'm going to do AMD GPU.addTime. Here, B is equal to rock array of A. Took 1.17 seconds. Note that that's smaller than the time it took before, which is, about the same. It didn't actually matter too much. 1.17 versus 1.18. But look at the allocations here, like 3.7. Okay, it's actually giving us the same numbers. Sometimes these are different between at time and GPU, like the GPU package. At time. Sometimes it gives you different numbers. In terms of visualizing like what's actually happening on the GPU, the best thing you can do is probably just grab an NVIDIA GPU and run the code on an NVIDIA GPU, and then go through NVIDIA's Nsight diagnostic tool, and it will give you all the information you need. That's actually the best way to do it. But we have some simple commands to give you that information on Julia's side. For any reasonably sized problem, the compilation time isn't likely to grow as quickly as the computation. Yeah, that's generally what we assume in Julia as well. Any advice to an 18-year-old who wants to get into tech? I'm not going to go into too much here because this is a general purpose lecture for GPU computing, but what I will say is just start programming. That's the number one way to do it. I know it sounds very daunting, but just jump into programming. Being on Twitch and listening to other people talk about programming is a really great way to start. Just listen to people, enter the conversations, find a project that you're passionate about doing, and try to figure it out. You might not be able to figure it out, but in the process of trying, you will eventually get to the point where you can start to reason about the problem in a better way, right? It's really just about jumping in the water and going for it. Okay, back to GPU computation. So we have A, we have B. What I'm going to do now is I'm going to talk a little bit about one of the abstractions that we wanted to introduce, and that abstraction is called broadcasting. I'm going to spell it out here, broadcasting. Okay. Now, the book I'm writing is called the GPU Kernel Handbook, right? So you might think that I care about kernels, and I do care about kernels. But when it comes to GPU programming, it's not all about kernels. You also have to deal with other ways in which you can access the GPU, right? One is to take a for loop, a while loop, and to extend that to GPU programming. Another is to use other things that exist in your language. Broadcasting is one of those, and to use that for GPU computation. Remember that a GPU is a separate device that is built to do a lot of simple operations at the same time, right? And so we need to basically find tools that allow for us to manipulate the data on the GPU and use that data to the fullest extent. When I do Julia T12, I get 5 threads. When I do T8, I get 14 threads. That is insane. Yeah, you need to, it seems like it needs management threads or so. I don't know what's going on there, to be honest. T12 always works for me. So you said are you running NICs? There might be some NICs issue, but if that's the case, I think that's something you need to bring up to like the broader Julia community and ask. So go into the Julia Slack and ask there, because this might be an issue that we just need to solve and no one has solved it yet. Okay. So I think as we start talking about what we can do with the GPU array, let's just start there. Okay, so we have an array, A. And let's say I want to change an element of A, like the first element of A, and I want to set that equal to 1, okay? Now if we do A, we have all zeros except for 1 up here in the corner, right? Now let's try to do the same thing with B. B is our GPU array. We do B of 1, and what do we get? We get a scalar indexing is disallowed error. This is kind of a bait and switch type of situation. I actually brought this up for a reason, right? And that is that if you want to manipulate a single index of B, your GPU array, this is almost always going to be a bad idea. Because remember, the GPU is built to do a lot of operations in parallel, not just one or two things, right? And so if you want to do just one or two things, like B of 1 is equal to 1, B of 2 is equal to 2, or something like that, probably you want to transfer that over to the CPU and do all of these individual things and then transfer it back to the GPU. There's very few situations where you actually want to do one index at a time. For a GPU array. And the reason we expressly disallow this type of indexing is because there could be a situation where someone is writing code and they just accidentally do this. They don't mean to do this. And in the process of accidentally doing this, they cause computation, which is slow. And unfortunately, due to the the composability of Julia and how the packages talk to each other, it could implicitly transfer data from the GPU to the CPU to do this type of stuff without the user knowing, right? And so we have to be very explicit. Like when you are accessing just a single element of a GPU array, we don't want you to do that. Now, there is a way to fix that, right? And the way to fix that is by setting scalar indexing to be allowed by using allow scalar or @allow scalar. So if I run the same command with @allow scalar, I think AMD GPU. Okay, actually, I don't know where it is. AMD GPU dot something. Maybe it's just @allow scalar. It should work, but it might not work in AMD GPU right now. There was actually an issue that I brought up the other day for AMD GPU about this. Let me see where that one went. Julia. Let me go to issues, and let's go to allow scalar. Oh, you know what? Probably because I'm using an older version of GPU, of AMD GPU. That's why this didn't work. Yeah, let me see what I got here. This. Yeah, that's what it is. Okay, right. Yeah, okay. So because I'm using an older version of AMD GPU, this doesn't work, but in future versions it will. Sorry, there was a bug that had to do with AMD GPU. That for some reason this just doesn't work the way I intended it to. But I think if we do AMD GPU dot allow scalar, this will work. Yeah, that works. But they also say that you can use an AMD GPU do block. Where, one second. Let me try this again. B of 1 is equal to 1. So they also say to do allow scalar do block, which would look something like AMD GPU dot allow scalar do, something like this. And this one somehow works, but I thought it wasn't going to work. Anyway, point is there's sometimes some finickiness for allowing scalar operations. I don't know anything about it, but as a hunch, can you do B is equal to A? So you can technically do B is equal to A. But this is doing something different than what you might think. So if I do this, now all of a sudden B is no longer a GPU array, B is now a CPU array, right? This is a matrix as opposed to what it was before when I did rock array of A, it's a rock array. So we transformed it into a CPU array. Let's talk about how to do B is dot equal to A though, because that brings up the next point, which is broadcasting. When would you specifically want to allow scalar? So there are some situations where you want to do scalar indexing, as in, like, if you do a summation and you summed everything into a single element, right? Then you just have one element that you want to read back. That's a situation where you might want to do allow scalar. Basically, anything that requires, like, there's a lot of different operations you might need it for, but it's ultimately very uncommon, and the most common approach is to transfer the data back to the CPU. Okay, so let's talk about some stuff you can do with Julia. And this actually brings up what Kaz Games is talking about before with B is equal to A. B equals A does not do what you want it to do. But if you do B is dot equal A, all of a sudden, it will work as intended. So let me just talk about what we're doing here. So there's a concept in Julia called broadcasting. I'm just going to work off of the array A. So right now the array A is basically a 10 by 10 matrix with a 1 in the corner. I'm going to redefine A. A is going to be equal to 1s this time of, let's do 10. Okay, so now it's just 10 1s. Okay. Now what I want to do is I want to modify the data in A to be something else, right? To do this, what I'm going to do is I'm going to say A is going to be dot equal to 5. And now it's all 5s. Now, this is something called broadcasting. What it does is it takes a single operation, in this case, setting everything equal to 5, and it broadcasts it to every single element in the array. So it takes equal to 5, and it sets A of 1 equal to 5, A of 2 equal to 5, A of 3 equal to 5, A of 4 equal to 5, so on and so forth, right? On the CPU, this is done iteratively. But on the GPU, we play some magic tricks, okay? So that if we do B is equal to dot equals A, this one's actually going to work. It's going to take a second to do pre-compilation, but this one will work, right? Because we're not just taking 1 index, 2 index, 3 index. What we're doing is we're transforming this broadcasting command into a GPU function that now works on the GPU, right? And so what we've done is we've taken the Julia syntax, which is already meant to work on an array, and we've transformed that into a command that is now meant to work on every element at the same time, right? And if we're taking something that has, if we take a function that's been transformed to work on every element at the same time, well, that is now exactly what the GPU is made for, doing a bunch of operations, a bunch of simple operations on every element of the array at the same time. That's exactly what the GPU is made for. And so what we've done is we've taken the scalar indexing issue, which is obviously we can't take 1 or 2 elements, but we said, okay, but if we take a bunch of elements at the same time, it should be okay, because this, in essence, is what we want to do with GPU computation to begin with, right? And so this broadcasting specifically allows us to set or manipulate GPU arrays by essentially magically. It's not. I mean, it's not magic. It goes through the GPU arrays.jl package. It transforms it into a GPU function for us. So yeah, you can do exactly. So if you do b, so you can't do b dot equals a plus b because a and b are in two different. Here, let's just show that off. A plus b is not going to work. Okay. Well, let's set b is equal to rock array dot zeros of 10. Sorry, AMD GPU dot zeros. Okay, so now we have A, which is a bunch of 5s, and B, which is a bunch of zeros, and we can't do B plus A. And the reason we can't do B plus A is it's going to throw in an awful warning, an awful error message. But the big reason is you can't do this because A is not of the right array type. So argument 4 of your kernel, base broadcast is AMD rock array blah blah blah. Where is it? Is of type. It gives you an awful warning, but this warning is essentially saying the reason you can't do A plus B in this case is because A is on the GPU, or A is on the CPU, and B is on the GPU. There are two different memory locations. We probably should make this particular error message better, but it's quite difficult to do because it's going through the whole broadcasting ecosystem. So that's not able. You can't do that. But we could, for example, create a new array, which is C, and this is going to be equal to rock array of, I don't know, rand of 10 or something like this. And then we could do C dot equals B plus C or something like this. And that one will work, right? And we can just keep doing this as much as we want, right? So, yeah. The point is that, like, as long as the arrays exist on the same memory location, like they both exist on the GPU or they both exist on the CPU or the same GPU, then it's totally fine. How would you do maths on each element? Like multiplied by 2, b dot, yeah, exactly that. So you could do the following. So you can do b, let's set b is dot equal to 1 for now. Let's do 2 for now. And now we're going to do b dot, this equals 2, okay? And what that will do is it will raise everything to the power of 2. We could also do dot times here. Oh, that was an 8. Dot times or dot plus, right? This will all work. Dot plus equals works. All that's totally fine. So A is equal to B plus C. You can do A is equal to B plus C, but that's going to create a new array. What you want to do, okay, this is a trick, and it's a trick that I also mentioned in the book. There's actually a big difference between C is equal to, here, let's go back up here. So we did before, we did C is equal to B plus C. We did this, dot equal to B plus C, okay? And now I'm going to do C is equal to B plus C. Now, to the untrained eye, these look identical, right? They should be the same command. But there's actually a catch here, and that is that this one right here is creating a broadcasted function. What it's doing is it's saying we take every element of C, and what we're going to do is we're going to set every element of C to the following. So it's like C of, let's say, IDX is going to be equal to B of IDX plus C of IDX, right? That's what we're doing with the first command. In the second command, what we're doing is we're saying B of IDX plus C of IDX. We do all these together. And then after that's all done, we create a new array and set that equal to C. So it's very subtle, but what's happening is this is an in-place operation. What that means is the memory that has existed in C, right? That location for C, right? We're individually going through each each individual element of C, and we're adding B of IDX plus C of IDX. In the other case, C equals B plus C, we're actually going to do the addition and then replacing the old version of C with a new array, right? So, case in point, if I set this to some array D, this will work, right? But if I did E dot equal B plus C, that will not work, right? Because this one is creating a new array D, and this one is taking elements of E and adding and modifying each element of E, right? This is very subtle, but this one did not work because E did not exist beforehand, whereas this one did work even though D didn't work. It didn't exist beforehand. Is this making a little bit more sense? So again, this one works out of place, whereas this one works in place, right? Is rock array deprecated? Oh yeah, so if you're using CUDA, just for the record, let me just go ahead and write this out. If you're using CUDA, then what you want to do is use CUArray. If you're using, that's not what I meant to do. If you're using metal, then what you want to do is use MTL array. And if you're using one API, you want to use a one array instead of rock array. There's also one other thing that you can do. If you still don't know the hardware that you're running, you can also do the following. Add CUDA, one API, metal, AMD GPU. You can add all of them, right? And if you add all of them, then what you can do, okay, I have some issues as to why I can't do that right now. But if you add all of them together, then what you can do is you can do AMD GPU dot functional. Oh, I have to use, you can do using AMD GPU and then AMD GPU dot functional here. And this will tell you what works and what doesn't. So if you still couldn't figure out your hardware based on all the other ways that we were talking before, you could just download all of the packages and then just try to see if any of them are functional or not. And this will tell you what works. Can you make a huge random array and multiply using the GPU then CPU to see the differences, the time differences? Yeah, we're going to do that next, actually. So let's talk about timings. Okay. So one other thing I want to talk about for broadcasting is that it not only works for like generic math functions, but it works for any function. So if we create a function f of x, and this is going to be equal to x plus rand, let's say. Cool. I can distribute that across a. So I could do a is going to be equal to zeros of 1 of 10. And then I can do f dot a. And what this will do is it will basically take the elements of a and it will add, it will do the random function that I created before. So it will add a random number to it. Note that it didn't update a in place. So to make sure that we can do this, we have to do a dot equal to f dot a. Right. And so this does everything we said before. It takes the structure that is a, it goes into each individual element, and it adds a random number to each of them. So if I keep doing this over and over again, we're basically adding a bunch of random numbers to a. Okay. So let me reset a now. A is going to be equal to zeros of 10, and b is going to be equal to see AMD GPU dot zeros of 10. Just to be clear, this also works on the GPU. So let me just do the same command on the GPU just to show it off. And now I'm going to do exactly what Kaz Game said. And actually this is also in the book, and it's, you know, the exercise that's 1,000 times faster on the GPU versus the CPU. So let me just do b is dot equal to f dot b. And this will work, and we can just keep doing that. Okay. So now let's create a situation where we see a very clear advantage for the CPU and GPU, because this is actually a question I get a lot. So many times I talk to people about GPU computing and they tell me like, okay, I'm doing like a very simple addition, like a vector addition, like we just did before. Like when I did b dot plus b, right? I'm adding b together. When I do this is called a vector addition. I'm taking two vectors and I'm adding them together. I do this, and for some reason, it's not faster. Like the CPU is faster. In fact, let's just do that. Let's do AMD GPU dot at time b dot plus b, and now we're going to do at time of a dot plus a. Okay, so if we look at this, okay, actually even in this case we see the GPU is a lot faster. Oh no, okay, we had to wait for pre-compilation. So we ran it once, we did pre-compilation, right? Because 99.94% time is compilation time. And if we do AMD GPU dot at time b plus b, we actually see that in this case, the AMD GPU, my GPU, which is supposed to be really fast, is literally, what is that, 50 times slower than my CPU. So what's the deal? Why do I care about, like, why would I ever do GPU computing if, in this case, the CPU is faster, right? And actually, there's, you know, for these very simple operations, I've said time and time again, when you do GPU computation, it's this balancing act, right? It's a balancing act between having a simple enough operation that the GPU can handle it, and enough of those simple operations that the GPU can actually excel at doing that thing, right? And so it's a balancing act between complexity, and when you hit that balancing act right, the GPU is incredibly fast, but it's not necessarily always going to hit that. And you have to make sure that your problem is actually well suited for the GPU. I missed the beginning of the stream. Is rock array an array for rockm? Yeah, so it compiles down through the rockm pipeline. One value is 7 precision, the other 6. That's strange. Yeah, I don't know where that was, but I think I know what you were talking about. A is only zeros though. That's true. I mean, we can change what A is. You're right. I should have done that. So let's say A is going to be equal to rand dot equal dot plus equal. 1 second, rand. There we go. Oh, obviously, it's the same rand number. Okay, 1 second. A is going to equal to rand of 10. I'll get it right one day. Now we're going to do A dot plus A, and we're going to do at time that. And we can see it's still insanely fast. And keep in mind these numbers are really small, right? They're very small, right? And so it's very difficult to make like judgments on any type of computation when it's this small. So let's create a situation where we can definitely see a clear advantage for using the GPU, okay? So we're going to create an array. A is going to be equal to rand by 19, let's do 1920. I think 1080 by 1920. Okay, now what I'm going to do is using plots. Oh, now we have to add the plots package. So we go back into the package manager and add plots. And again, if you don't want to do the package manager, you can do like we did before, using package and then package.add. I'll show that off in just a second. The CPU is not using SIMD in this case. It was just single-threaded CPU, so just a single core. So it's like the setup time for SIMD, add extra time, and it's only worth it if you have enough values. That's exactly what it is. You need enough values to justify using the GPU. It needs to be a big enough array, a large enough number of these simple operations. Does Julia do manual or automatic garbage collection? It does technically automatic garbage collection, which does kind of suck for a lot of cases. But what I always tell people when it comes to garbage collection is that as long as you're not invoking the garbage collector too often, it's fine. So like basically like when you're doing manually memory allocated languages, like you have to manage that memory on your own. You know, you care a lot about each allocation because you physically have to do it. Which with garbage collected languages, okay, yeah, sure, you don't technically have like the allocations and the freeing don't happen manually. Well, the allocations probably still happen manually, but you know what I'm trying to say. Like, you don't have to free everything. But at the same time, you should care about your memory, right? There's a reason why at time, you know, always shows the number of allocations. At time A plus A, okay, it didn't in this case, but it will also give you, yeah, it gives you the number of allocations because even though it's a garbage collected language, you still care about allocations. And as long as you are careful about allocations, the garbage collector usually does not turn into a huge issue. Can you pass an argument to only time, not compilation? Usually what people do is they just run it twice, because you have to precompile the function first. You can also do like an at benchmark to get rid of that and stuff like that. I'm not aware of a single of something you could do to run at time and like just avoid pre-compilation. Is GPU computing reasonable for maximum likelihood estimation? I think so, but actually I've never done maximum likelihood estimation, so I'm not entirely sure. Okay, so here's what we're gonna do. We created a giant array. I'm gonna do it again. A is gonna be equal to rand of 1080 by 1920. Now, we installed plots. Again, if you weren't able to get into the package manager, you can just do using pkg, and then pkg.add plots with a capital P. Like that would also work. Now we do using plots, and what I'm going to do is I'm going to heat map A. So I'm going to run heat map on A, and you'll see we should have just a random matrix. Here's a random matrix. Wow, a bunch of random numbers. Isn't that cool? And now we're going to play a magic trick. We're going to make this array of random numbers disappear. How are we going to do that? Well, we already have a function. F of x is going to be x plus random, right? And so what I'm going to do is I'm going to say for I is 1 through 1,000. I'm going to say a is dot equal to f of a. Okay, so what I'm doing is I'm using this function, f of x plus random. I'm using this 1,000 times. I don't know why I went up here. Let me just write this. For I is equal to 1 to 1,000. We're going to a is dot equal to f dot a, and end here. So we're running this function 1,000 times on a, right? And now what I'm going to do is I'm going to do a dot divided by 1,000. And now if I do heat map of A, we see, oh wait, I have to do one thing. I think I have to do with clims is equal to 0, 1. There. Now we see that, wait, why is it all 1? Did I do something stupid here? 1 second. Yeah, that should be right. Wait, I did something stupid. All these are 0.5, right? What am I doing that's dumb here? Heat map of A. It should all be 0.5. But, A. Oh. I didn't do dot divided by equal. There we go. And now we do clims is 0 to 1. Okay, there we go. I didn't set them equal to 0.5. So what we did is we took a random array and we made all the values disappear. Whoa! So basically what we did here is we randomly sampled 1,000 values, right? And we averaged them all together to get 0.5. That's what we did. And yeah, what clims does is it clamps the values from 0 to 1 so that we can see that precision, see it basically all 0.5 at the same time. Okay, so now what I'm going to do is the same thing for B. So we set A is going to be equal to rand here. And I'm going to do AMD GPU.rand. And we're going to do B is equal to this. And then we're going to do the same for loop we had before. And just for the record, guys, in Julia, if you press F and then up, what this will do is it will go through all of the last commands that had an F to them. So you can like look for F for I is equal 1 through 1,000, F of X, all this kind of stuff. But we'll write it out for now. For I is equal to 1 to 1,000. We're going to do B dot equal to F dot of B. And we're going to end there. And now we're going to do B dot slash divide equal to 1,000. And now we're going to do a heat map of B. Now note, this should fail, I think. Yes, because we haven't sent it to the GPU yet. Sent it to the CPU yet. So we have to do array of B. And then we also need to do clims is going to be equal to 0, 1. And this should give us the same value as we did before, right? So why is this interesting? The reason it's interesting is because of the following. So we just did 1,000 very simple kernel launches. Each kernel launch is basically modifying a single pixel value. That's what we did. So what do we think about timings here, right? In principle, this is a high definition image. We should expect CPU timing to be okay, but this is where GPU timing should shine. So let me go back to the for loop I had before. This is for A. I'm going to do at time A. Okay? That's like 1.56 seconds. Now I'm going to go back to the for loop I had before for B, and I'm going to do AMD GPU dot at time this. And we see it's 0.006 seconds, right? And so this is a situation where, you know, from the testing I did before, it's like 1,000 times faster. I guess in this case, it's 500 times faster. But it very clearly, this is a situation where we took a high definition image, modified every single pixel in that high definition image in a very simple way. And we saw some very, very high performance benefits for using the CPU in this, or using the GPU in this case. Now, I have something I need to mention, some jank in the Julia ecosystem that, I just have to mention. And that is that when I did A dot equal to F dot A, well, rather, when I did B dot equal to F of B, this created a GPU kernel that was parallelized on the GPU. It used all my GPU cores, and it works just fine. When I did this for A, it actually only did single-threaded execution. This is actually an issue we have with Julia right now, where doing broadcasting is not naturally parallelized. It should be naturally parallelized, but it's not right now. So we're comparing, in this case, not necessarily, parallel GPU to parallel CPU. We're comparing, in this case, parallel GPU to single core CPU. So if I was using all 12 threads, this would be 10 times faster, and it wouldn't be, it wouldn't be 1,000 times faster. It'd be like 100 or 50 times faster, which is more in line what you expect from parallel CPU execution to GPU execution. So a little bit of a disclaimer there. Let me catch up on chat here. Random question. What did you consider one of the most profound ideas? I don't know for sure. I don't know if I have an answer to that. Does it clamp the values? Yes, Mr. GPU guy. Can you tell me how hardware acceleration works in web and WebGL, and how we're able to run high quality and performance heavy games? So this goes down the graphics pipeline, which I talked about a little bit earlier. But web GPU, I've never used it, but from my experience, is more or less like Vulkan in a way, and that is it is a performance portable language that allows you to do GPU graphics across different hardware vendors. So it's kind of the same as OpenCL or Julia or something like that, in that it compiles down to some lower level intrinsic language, I assume. It just happens to be that you're calling this language from the web instead of calling it from like Julia or C or something like that. Does it make the browser have direct access to the GPU? I think it's the same as like JavaScript or something like that. I'm not entirely sure, but I'm pretty sure it's the same as like JavaScript, where it's like the higher level language that you're using happens to be however you're using web GPU, and then it ends up calling the hardware under the scenes. Hey, Justin, how are you? I saw your video recently. Good job on that. Is your book available somewhere? Yeah, the book is currently available. Can I just press up? Can I paste it here? Yes. So this is a chapter I'm working on right now. And again, I'm going to post it on YouTube as well. So yeah, the book is currently available right there. The chapter, the stuff that we're going through right now is all available there. So just for the record, I'm going to go through the book right now just to make sure we caught everything. So what we've done so far at this point is we've talked about all the different ways to GPU. We installed Julia. We figured out the hardware that we're running. We talked about our first GPU array. We talked about performance expected from Julia. We talked about scalar indexing. We talked about broadcasting. And we did our big example showing that we can get 1,000 times performance benefit from using the GPU in this case. Now, I've been talking for like an hour and a half now, and I don't want this lecture to be so long. Luckily, the next section is not as long as the section that we've gotten up. We've gone through so far. Yes, it is technically talking about kernels, and the book is called the GPU Kernel Handbook, which is to say the majority of the book is talking about kernels. But because the majority of the book is talking about kernels, I felt it was okay to lightly introduce them here and then talk about them more in more depth later. You look wise. Let me ask one thing. How do I get rid of AI? Wait, how do I get rid of AI will replace you anxiety? I mean, so far AI is crap, but when I assume in the future it will be useful for something, and as it becomes useful for something, it can't replace researchers. I mean, like there's certain things that it can't replace, right? And because I do research, I've never felt AI will replace me. Maybe in some scale, like I felt like, oh, maybe AI could write better poetry than I could. I like writing poetry. It's sad that people won't read the poetry I write. I don't know, but it's not. I feel like as AI becomes better and we're better equipped to using AI, people will find more tools. We'll be able to move at a faster pace, and we'll find other niches that we're able to do. I don't think this is as big of an issue as other people are saying. Sure, it might hurt a few areas in the short term, but in the long term, having more tools available to do more tasks has ultimately always benefited society in the long term. So no need to worry about AI. If you keep studying, it won't replace you. Yeah, this is kind of my opinion as well, but I'm naive here. What did you use to write the book? It looks pretty. So right now I'm using just documenter.jl. It's just a Julia package to do documentation. I quite like it as well. Learn to code, learn to pivot. Yeah, maybe pivoting is what we need to. Either AI will be a great tool when we adjust to it, or it will murder us all, and then nothing matters anyway. I feel like murdering us all, yeah, maybe. I mean, because AI could really help with war. But anyway, we're getting really off topic. I think of it like this. It will replace your partner, but not you. Your partner. Anyway, long story short, let's not talk too much about AI. This is not an AI stream. This is talking about GPUs. I do recognize that one of the core applications of GPU programming is for AI, but that's not the intent with this this series. Okay. I do have one other thing that I mentioned here in the book, and that's final musings about broadcasting. So we introduced this thing, and I showed that it's incredibly fast, and it works very well on the GPU. And in fact, there's a whole bunch of packages that rely on broadcasting in Julia without ever having to write GPU-specific kernels. This is because through the GPU arrays.jl package, if you do broadcasting, you get the performance you want from the GPU just by writing code in like a way that seems natural, right? Like a dot plus equals, one second. Sorry. B dot plus equals 5. I mean, that's natural. This is math. You're just doing math, right? And so if you can write your code in a way that looks natural, like to mathematicians, basically you can use broadcasting for 90% of the applications that you need to do. And I myself find that I use it a lot for various things. Like for example, when I was writing a molecular dynamics engine, I used broadcasting for the actual movement of the particles. Now, in terms of finding the forces on the particles, I had to write a GPU specific kernel, but there's applications where you just surprisingly use this all the time. And there were certain applications that I saw, when I entered MIT for the first time, of people using broadcasting exclusively. Like they never had to use a kernel for anything. They never had to use a GPU function for anything. Because broadcasting was so powerful, they were able to use that exclusively. And you see this a lot. So the reason I brought this up is not necessarily because it's the best abstraction for GPU programming. It's because it is a good way to get your feet wet, to just try it out, see if you can do it on your machine, all this kind of stuff. And not only is it a good way to get your feet wet, but it also is powerful enough that I find myself using it, even though I also have kernels available to use, right? And so that's why I brought it up. So now we're actually going to start in, talking about like real GPU programming, okay? Again, we're lightly covering it today because the rest of the series is going to be talking a lot about kernel programming. So it's okay to just introduce the basics today. To do this, we're going to be adding the kernel abstractions package. So first we do, instead of opening up the package manager, I'm just going to do using pkg. And I'm going to do pkg.add, add kernel abstractions. All right, so we have kernel abstractions added in. Give it a second. Using kernel abstractions. 1 second, I have to cough. So we have kernel abstractions loaded. What can we do with this? Well, let's go ahead and do vector addition. Like we said before, it's like b dot plus, okay, let's do vector addition. So here's what we're going to do. We're going to do vector addition first via broadcasting. Yes, so that's exactly what broadcasting is doing. It is actually creating a simple kernel under the hood. If you look at gpuarrays.jl, you can see that happening. But it literally just takes this thing that we know should work element-wise in Julia and says, okay, let's just turn that into a kernel. And that's why it works so well. And again, it's parallel in the GPU, not in the CPU. Okay, so first let's do vector addition on the GPU. So what I'm going to do is Control D and open this up again. I'm going to do using AMD GPU. And I'm going to create 3 arrays. A is going to be equal to AMD GPU.rand of, let's do 10. B is going to be equal to AMD GPU.rand of 10. And this time I'm going to do something. I'm going to put a semicolon here. What the semicolon does is it says to just don't output into the REPL, right? So basically it removed this output here. So don't automatically output that. And now I'm going to say C is going to be equal to similar of A. Okay. What similar does is it basically allocates data, like allocates the space for this array on the GPU or on the CPU, but it doesn't necessarily do anything with that data. So when I do this, C is all like zeros, but it could be anything. It's just whatever was sitting in memory at the time, right? So basically I allocated C, but I didn't write to it. Now we're going to do C dot equal to A plus B. Okay. Again, you want dot equal to, not equal to, because this would create a new array C, whereas this uses the pre-existing data for C. So this is vector addition on the GPU with broadcasting. So now we're going to do the same thing, but this time in a kernel language by writing a function for that. So let me write a very simple function. I'm just going to say add, and it's going to take 3 values. It's going to take C, A, and B, and I'm going to write this in a weird way. We're going to add index by index. So it's also going to take IDX. And what we're going to do is we're going to say, function add. We're going to say C of IDX is going to be equal to A of IDX and plus B of IDX. And then I'm going to end this down here. Now I'm going to do a couple of weird things here. One, I'm going to add an exclamation point here. Now, you don't necessarily need to add the exclamation point. This is really just notation. What this does is it allows other people to know that this function mutates data. What does that mean? It will take your array, C, A, or B, and it's going to change the values in C, A, or B. It's not going to create a new C. It's going to use the data that already exists, but I want to let people know that the C before this function and the C after this function might be different. And notationally, this is also why I put C before A and B. In general, in Julia, just to let people know that the data is going to change, you put the argument that's going to change at the start, and then you also put an exclamation point to let people know. So now if we do add here on C, A, B, and we take the first element, 1, we've now... Scalar indexing is disallowed, remember? Yeah, okay, that's not going to work because they're GPU arrays. But if these were CPU arrays, this would work. So let's just do that on the CPU first. So we're going to do A is going to be equal to rand of 10. B is going to be equal to rand of 10. C is going to be equal to similar of A. And now we're going to do add here of C, A, B, 1. And there we go. Also, one thing I need to point out, I'm going to create 3 new arrays. So A is going to be equal to AMD GPU, A. B is equal to this, and we're going to say GPU B. And C is going to be equal to similar of A, so GPU C is GPU A. This is something that I probably shouldn't point out, but I'm going to point out. We can't do B of 1. GPU A of 1 does not work. But if we do GPU A of 1 to 1, which is a range between 1 and 1, this will work, right? And similarly, we can also do any type of broadcasting on ranges. So for the record, we can do 1 to 5. We could do GPU C from 1 to 5 is going to be equal to GPU A of 1 to 5 plus GPU B of 1 to 5. And again, we have to set this. What's going on now? My shell froze. What is going on? Okay, hello. That was weird. 1 to 5. And we're going to do dot equal here. And now we see that if we look at C, oh, right, because, okay. If we look at GPU C, we'll see the first 5 elements are now of C plus B, right? And that's what the ranges do. They allow you to grab specific groupings of these different arrays. There's no new allocation or duplication of memory. It's not pure. Was it the shell or rather the terminal? I don't know what was going on. Maybe the Julia REPL was having some trouble. I'm not sure. Let's see. Do you have to worry about leaving data in memory? Could another process read it? I guess in principle, another process can read it, right? But in practice, I've never really worried about this. Maybe I should. Okay, so we have this function that I created before, and we said add C AB1, and if I look at C now, we see the first element is what we expect. So 2, and then we look at C, now the first 2 elements are covered. If we do 3, now the first 3 elements are covered, right? So if we do C here. So in general, we could create a loop, and we could look through all the elements of C. So for I is equal to 1 to length of A or something like this. We'll do add here of C, A, B, I, and here, and if we look at C, okay, we just did the addition. This is a very stupid way to write this function, but I wrote it this way so that we can start talking about kernels. So using kernel abstractions, okay? So now what we're gonna do is we're gonna take this function and we're going to turn it into a GPU function. So we have add function, add here. So what I'm gonna do is I'm gonna do @kernel, which is going to signify that we're transforming this function into a GPU function, right? Now, to transform a normal function into a GPU function, we're already most of the way there. We have C, A, and B, which work on arrays. They're array level. And like I said, when we do GPU programming, we focus on arrays first and foremost. The only weird thing is that we have this IDX in here, right? And when I tried to use this before on C, A, and B, you noticed it doesn't work if we run with an IDX, right? Well, that's because what we have to do is we have to take this IDX and we have to move it into the function itself. So let's go here, and we're going to say IDX is going to be equal to @index global. Now, what does this mean? What does this command mean? Well, basically what we have is we have a list of threads, a list of cores, right? And what we want to do is we just want to say, look, I'm just going to grab all the available cores that I have, just from the global thread bank, all of the threads that are available. I'm just going to grab an individual index, and I'm going to work with that index, right? And so what we're doing is we're taking this function, and we're saying, okay, core 1, you're just going to be IDX1. Core 2, you're IDX2. Core 3, you're IDX3, so on and so forth. It doesn't matter when you run these. I don't really care when you run these. Just run them when you can. But you, core 1, are always going to be 1. Core 2, you're always going to be core 2. Now, no, there aren't really that many cores, right? There's only like 1,000 cores. What if you have to add like 1,000 elements together, or 10,000 elements, or 1,000,000 elements together, and we don't have enough cores for that? That's okay. It doesn't really matter, because what we do here is instead of talking about cores, we talk about the software abstraction for cores, which are called threads. So we as users don't have to think about this, right? We say, okay, instead of core 1, we say thread 1, do this. Thread 2, do this. Thread 3, do this, right? And so this individual function can be run on every individual thread, and the threads just have some idea of what number they are. And then they do the computation for you. So we're going to end here, and now we have a kernel. Add. Cool. How do we run this kernel? That's a good question. So one thing about kernel abstractions is that it runs heterogeneously. Heterogeneously might not be the right word, but it can run on any hardware, right? And so what we have to do is we have to figure out what backend we're running on. So to do that, we say backend is going to be equal to get backend on A. This is going to be CPU backend. And if I do GPU of A, we're going to have a GPU backend, which is a ROC backend, right? So I'm going to do this twice. We're going to do backend of 1, CPU backend is here, and we're going to have a GPU backend. Okay? Now I'm just going to launch the kernel. So to do this, we need to first configure the kernel. So we'll do add kernel. Let's do CPU kernel. is going to be equal to, again, this is going to mutate data, add here of CPU backend. Oh, and I need to give it some notion of the number of threads that I'm going to run with in a group. So to do this, I'm just going to say like 32 or something for the CPU. Should be fine. What did I do? At kernel, function add. That one worked just fine. And then this is going to be equal to CPU backend there. And it says no method matching add CPU. Well, let me try at kernel function kernel add. And let's try kernel add over here. There we go. So that one worked. And now we're going to do the GPU kernel. We're going to change this to the GPU backend. So now we have two different backends. One's for the CPU and one for the GPU. What's the false in CPU false? I don't remember what the false stands for exactly. It has to do with... I don't remember what it stands for, to be honest. I used to at some point, but I've forgotten. Sorry about that. I'd have to dig into the kernel abstractions code. Is there a bounded amount of threads, or are they arbitrary? It's technically arbitrary, but you bound it when you launch the kernel. So, sorry, I don't remember what it is exactly. So now we have the CPU kernel and we have the GPU kernel. Let's run this kernel. So we have CPU kernel here, and we're going to run it on C, A, B, like we did before. And now I'm going to add a special argument. This is ND range is equal to length of A. Now, what is ND range? It's an n-dimensional range that you're going to be iterating over, right? This is pulling from OpenCL notation. If you have used OpenCL before, if you haven't, it's okay. But it's basically saying when we're talking about how many threads are we running, basically this is how you determine how many threads are being launched, right? You just say when you're launching the kernel, this is how many we're going to launch. So we do this, and we see C as now A plus B. Okay, just to be clear, we're going to do this is dot equal to 0, and we're going to launch that again. CPU kernel with CAB. If we look at C, okay, the data is there. So now let's launch the GPU kernel. We're going to do the same thing. So we do GPU kernel, and we have to do GPU A, B, and C. Here we go. And ND range, just for clarity, we'll also put GPU A here. Run that. And now if we look at C, okay, it's A and B put together. Again, just to be clear, we're going to, GPU C. And now if we do GPU C dot equal to 0, and we do it one more time, just to be clear. Now we do GPU C. We see this, and I just want to test that this is true. So I'm going to do using test, and we're going to do at test. GPU C is going to be equal to GPU A dot plus GPU B. Should return true, right? And so what test does is it basically tests to see whether the output from a value is true or false. So we do at test of true, and at test false. There we go. Good. So this is kind of all I wanted to do for kernel programming today, in part because I'm running out of time, but also in part because, again, the rest of this lecture series is going to be focusing heavily on kernels, right? So it was okay to just introduce the syntax for today and then move on from there. And again, I've already been talking for 2 hours, so I want to cut this a little short from here. So the last thing I want to talk about is loop vectorization. This is the act of taking a parallel or taking a for loop and transforming it into, or a while loop, but transforming it into something. I guess it has to be a for loop, but transforming a for loop into something that can run on the GPU. To talk about this, I want to actually talk about the CPU loop and explain some issues I have with CPU loop vectorization, and then to talk about what you can do in Julia right now. So first, we're going to do for I is equal to, for Pete's sake, I is equal to 1 to 10, print line, I, end here. And now I'm going to show something that everybody knows. Oh, okay, maybe not everybody knows, but people who've done parallel computing before, they know what's up. So I'm going to do threads, dot at threads, and I'm going to launch this function again. Okay. Now this is something that initially surprised me as an undergraduate, and I think it surprises everyone when they do parallel computing for the first time, but is not surprising when you think about it. That is to say, the output for this is ordered 1 through 10. The output for this is not ordered. It's just whatever thread got to this particular like print line function first, right? Now, the reason I bring this up is because when we start talking about taking loops and turning them into parallel loops, we're not removing any complexity from parallelism. That is to say, if I want an ordered list here, I have to do something different than what I just did. You know what I mean? And so we still need to like write it all to an array or do something different, right? And I personally have my biases against, threaded loop execution because from my experience, what ends up happening is users don't properly grapple with the parallelism when you do like threads.at_threads or something like this. And it makes it so as you are writing this new parallel code, you are not, grappling with the fact that this loop is not iterative, right? This is an iterative loop. It does 1, 2, 3, 4, 5, 6, 7. This is not iterative. It's doing everything in parallel, right? And so what you end up doing is you end up writing this code where like, let's say for n-body simulations, which I brought up earlier, you'll have like, a function that's like, summing all the particles together and all this kind of stuff. And it ends up being like the middle loop needs to be parallelized for some reason, but the outer loop should be iterative and the inner loop should be iterative. And so first you have to figure out which loop needs to iterate over or needs to be parallel and which one needs to be iterative. And then not only do you have to figure out which one's iterative and which one's parallel, now you've kind of like added unnecessary complexity on that one loop that is parallel, right? And so now not only do you have a bunch of nested for loops, but you have a bunch of nested for loops where one is kind of different than the other for loops, but they're all kind of loops at the same time. You see what I'm trying to say? Like what ends up happening a lot of times when you do loop vectorized code for the GPU or for the CPU is that the code ends up looking quite, it's not spaghetti code, but it does not help solve the readability issue that your code already has. Like the reason people go for loop vectorized code is because they can take already existing CPU code, throw a threads.at_threads on top of it, and fine, it's going to work. But it doesn't help you in any way. It doesn't really help you because you still have to deal with, like for example, transferring data from the CPU to GPU, which was, somehow a difficult part. You have to deal with like, thread synchronization. You have to deal with, the different memory blocks within the GPU itself. All this kind of stuff you still have to think about. And when it comes down to it, we have broadcasting, which works really well for simple stuff. And then you have kernel programming, which when you actually have to think about the internals of the GPU, it's pretty good for that as well. But when you add loop vectorization in there, it's not very clear where this should exist in terms of like an abstraction to use for GPU computing. Now, you can technically do it in Julia. We have floops, we have Jack, and we have, sorry about that, and we have, there's one other package that you can use for this. Oh, there's GPUify loops, but that's not the one I was thinking of. There's also, there's another folds. .jl. So these are all packages that allow you to take an iterative loop and to turn them into something that can execute on the GPU. Of them, I would recommend folds and floops, and then GPUify loops, and then Jax, just because Jack's execution model is quite different than the rest of the Julia ecosystem. So you have to like reason about it separately than the rest of Julia. But in principle, you could do this if you want. So I'm letting you guys know that this exists. And the reason I'm letting you know this exists is because some languages, like for example, Cocos and Sickle, both standardize on this. Like their primary thing is taking loops and turning them into something that can run on the GPU. I don't necessarily feel like that is the best approach, but it is something that people do. And so if you're somebody that wants to have that, it does exist in Julia, but I'm not going to be focusing on it for the rest of this lecture series. Just in part due to my own internal biases, but also because I've never seen loop vectorized code that is actually clean and easy to read. It always ends up becoming a jumbled mess, and it's almost always better to extract out that loop into either a kernel or some sort of broadcasting operation or something like that, instead of like just turning a loop into something that's vectorized. But again, that's my own personal biases, and I acknowledge I might be a little bit, I'm not necessarily like, the person to listen to here. In terms of the book, I just couldn't think of a situation where I'd be using loop vectorization, but if there is a situation where that comes up, I'll reintroduce a section and I'll add more to it in the future, and we'll talk about it in the lecture series. Is kernel folding when you go down from 8 to 4 to 2 to 1 kernel? Yeah, so this is actually something we're talking about next, the next lecture when we start talking about summation and stuff like that. x86 assembly is not, we're not talking about this, that's a CPU thing, but in principle we might talk a little bit about SPIR-V, not necessarily like the like lower level code. Like AMD, for example, goes directly down into something like an x86 assembly type of thing, instead of going down into a lower level representation first. GCN, I think is what it's called. Okay, so that was 2 hours of me talking about GPU computing. I think we stayed mostly on topic for the entire time, but this is a really good place to stop because this is like 3 lectures in one. It's way longer than I was hoping for it to be. If you guys have any questions, comments, concerns, ideas, anything like that, feel free to let me know either here, right now, I can talk for a little bit longer, or let me know in the comment section on YouTube or Discord, or GitHub issues, or whatever you want to do. Just reach out in some way, and basically what I'm doing right now is I'm planning to do a new lecture on every chapter of the book as it comes out. Now, I don't know how fast the chapters are going to come out. It could be every week, it could be every month. I'm not entirely sure. So let me just go ahead and talk about that for now. So let me go here to github.com /leios /GPU handbook. Here we go. So right now, the chapters I have planned are the following. So we just finished up the abstractions and GPU quick starts. So we have summation, which is the next chapter, which is going to talk about, summation is one of those things that should be somewhat trivial. Like, it feels trivial coming from CPU land, but it's actually very not trivial. Well, it's still easy in a way compared to other things you could do on the GPU, but it's not. You have to think about it for a second, right? And so I always talk about it as one of the first things. So summation, histogramming, to talk about atomics, and I'm also going to talk about Gaussian splatting there. I want to talk about transposition, data flow, and shared memory, and all this kind of stuff. I want to talk about the Box-Moeller transform, to talk about warp divergence, which is where one thread is doing one thing and the thread right next to it is doing something else, which causes, the threads to wait for one thread to finish. It's like a weird thing for GPUs. I do want to do an integrated n-body simulation. I like that example. I think it's really easy. We've already done it before on this channel. I'll talk about convolutions and a simple shader, along with FFT usage. And then I have to find something to do with BLAS. So if you guys have something that you want to do with BLAS, like the linear algebra library or whatever, just let me know. I haven't quite figured out what I want to do with BLAS for this, but these are like the big chapters. I also kind of want to do a chapter on signed distance functions and a little bit about metaprogramming. I really want to talk about metaprogramming, but I understand that's not everybody's cup of tea. Do other languages have macros that are that powerful? I'm not really familiar with things like threads.add-threads. So this is where when people brought up OpenACC and OpenMP, technically these exist in C to do very similar things. STS, by the way, or assigned distance functions, are ways to do kind of like ray tracing level graphics purely via mathematics, and it's quite nice. Maybe gradients with BLAS. Yeah, gradients could be useful, but if we talk about gradients, I kind of want to do autodiff type of stuff, but maybe autodiff is something, well, yeah, we could talk about that. I think gradients are useful. Yeah, thanks for coming in, guys. I really do appreciate it. Let's see what we got here. So again, in terms of the future plans, I'm not sure when these chapters are coming out. Some are going to be longer than other ones. Like summation should be kind of quick, but all of the future chapters have a lot more like graphics to make and all this kind of stuff, so they'll take time, Box-Moeller is already kind of done because I already have it on the algorithm archive, and transposition is something that I did for my thesis, so a lot of the stuff is kind of there, I have a perfect raid GPU live. I have no idea who they are, so maybe too unknown. Yeah, we'll talk about raiding in a second. I have to close off the YouTube first. Okay, so I think this is kind of where I want to stop for today. Again, if you guys have any further questions, comments, concerns, ideas, anything like that, feel free to let me know. There is a VOD available on my YouTube channel right now for people on Twitch, for those on YouTube. Again, feel free just to let me know what you guys think in the comment section. Once the GPU book is done, my intention is to get a whole bunch of reviewers. That would be maybe people like you, who either know or don't know GPU computing, who are willing to read the book and just let me know what you think. And otherwise, I want to talk to people at MIT and get them to read the book as well, so that they can give me some advice. Like, my worst fear is publishing a book with something wrong in it. You know what I mean? Like, I feel like I know my stuff. I've been doing this for 10 years. It's the only thing I really know. But at the same time, I'm not so arrogant to say that I know everything. And there's a lot of stuff here that, like, I could just accidentally say something stupid. And so I really would appreciate it if you guys could go through the written material here, read through it, try to do it yourself, figure out what works and what doesn't work, and just to do revisions, just to help me make the book better. Once all that's done, I do intend to sell a copy of the book, like a physical copy, both as a way to, because I think it's really useful to have a physical copy, but also as kind of a way to get a little bit of revenue on the side, as a way to help support the channel and future endeavors and stuff like that. So that's the overall goal with this book. And that, I think, is where I'm going to leave it for today. So thank you guys so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Leos Labs, which will be soon. I'm not entirely sure. I don't think the next episode will be for GPU programming. I think it's going to be something else, but I'm not entirely sure what that something else is. I'm kind of like, I just have a lot of different projects that I'm kind of balancing at this point. So I'll see you guys next time. I'm going to go ahead and close out the YouTube stream, and then I'll see if we want to raid someone on the Twitch side. So bye, YouTube guys. I'll see you again next time.